Dear community of scientists, dear experts, ladies and gentlemen, good morning and greetings to everyone, in fact, across the continent. My name is Martin Dauglis, and I am deeply happy as a moderator to welcome everyone to our conference Symposium Photon and Neutron Science in the Baltic Sea region, totally dedicated to enhancing scientific cooperation in the Baltic Sea region, infrastructures as the drivers of innovation, cooperation and interdisciplinarity. These days are going to be absolutely intense. Today we are in the first day of Symposium online conference where we're going to speak on mutual cooperation, common platforms where we can enhance the ideas and challenges and all things good we want to build up for common development. Tomorrow we are moving forward to matchmaking or the hackathon, also pretty intense day. The symposium will provide a good platform for discussing research ideas and challenges for preparing possible future collaboration projects through matchmaking. And if we speak on the keywords, then definitely sharing is the keyword of these days. We're going to share the common infrastructures we have, we're going to share common ideas and of course experiences, and a total good common discussion also will be keyword for these days. We have intense day today. The first part of the day will be totally dedicated to infrastructure experiences. We're going to share the possibilities scientists can have in particular laboratories. And then late afternoon, we will focus on the industry of science, sharing the content and possibilities from this content, building together infrastructures and science. Now is the particular moment when we are also looking on the opening remarks. So my pleasure is to give the floor to Klaus von Lepel, Project Director, Baltic Science Network, Free and Hanseatic City of Hamburg, Ministry of Science, Research and Equalities from Germany. Klaus, I hope you hear as well. The floor is yours and we are happy to have you here.
Yes, thank you very much, and a warm welcome from Hamburg as well. Dear participants, dear speakers, it is a pleasure to welcome you today to the online symposium on behalf of the entire Baltic Science Network. But first of all, I would like to say thank you. Thank you to Hella and her team from the Estonian Ministry of Education and Research, and to Agrita and her team from the Latvian Ministry of Education and Science for organizing the symposium during these challenging times. Thank you very much. You have done a really great job. Thank you for that. The COVID-19 crisis has greatly challenged international, regional, and also macro-regional cooperation in many spheres. It obviously also affects the work of the Baltic Science Network. With international mobility coming almost to a standstill, and the cancellation of conferences, of workshops, of seminars, we, as everyone else, had to rethink and to adapt our concepts. On the other hand, the recent one has also shown the great importance of science and research cooperation. International collaboration in research has greatly intensified in the span of just a few moments. The rapid mobilization of so many actors across the world to a collaboratively developed and collaboratively developed and test new therapies and vaccines against the COVID virus has been really remarkable. Also in the Baltic Sea region, we have seen cooperation in science and research did not come to a standstill. Meetings and workshops have been shifted to digital formats like our today's symposium, for example. And personal visits, research visits, has been taken place whenever possible, particularly during the summertime. And also we are working in different framework conditions at the moment. The value of science and research cooperation in the Baltic Sea is still unaffected, and the Baltic Sea remains one of the most competitive, innovative science regions in the world. Please allow me quickly to recap the status quo of science cooperation in the Baltic Sea region before the establishment of the Baltic Science Network to illustrate where we are coming from. The first CBSS Science Ministerial in 2016 marked the beginning of efforts to find a joint voice for science and research cooperation in the Baltic Sea region. Also, punctual cooperations in the field of researchers and research infrastructures existed before. There was no coordinated macro-regional framework for science and research cooperation in the Baltic Sea region. Furthermore, evaluation of Baltic BSN has shown that researcher consortia from the region were underrepresented in EU-funded projects despite the excellent research results. In addition, the examination of mobility flows in the region has shown that there's a significant amount of brain drain from the east to the west, and even from the western parts of the Baltic Sea region, furthermore to the west. The Baltic Science Network was founded to counteract these developments, in the belief that the Baltic Sea region countries need to cooperate and join their strengths and abilities for the region to prosper. At the start of the network, we focused, and therefore we created this kind of partnership with a multi-level governance structures with a lot of different players from all fields of science and research cooperation. At the start of the network, we focused on identifying challenges for science and research cooperation in the region. Numerous technical as well as high-level conferences were held during the last years to discuss and develop solutions and recommendations to fostering collaboration in different research fields. Studies helped to identify most important needs. Expert groups were formed on 3 thematic areas in research: photon neutron science, life science, and the future of the welfare state. And they developed concrete proposals on how to best support scientific cooperation in the Baltic Sea region in their specific area. A key asset of our project is that we have key stakeholders and decision makers of science policy on board in our consortia. With our mixed partner structure, we managed to obtain many different views on research cooperation in the Baltic Sea region. During the last year, Baltic Science Network has helped to put science and research cooperation in the Baltic Sea region on the agenda at all political levels: regional, national, macro-regional, and the EU level as well. But where do we stand today? With the Interreg-funded BSN Powerhouse project, we are now putting our findings from the first BSN project into practice. To foster cooperation and to develop research and innovation excellence in the region, 2 concrete support instruments are now implemented, tested, and evaluated. The first instrument, which Hella is going to tell you a little bit more later, has been developed by the BSN expert group on photon neutron science, the LaunchPad Research Infrastructure Connector. For widening participation of research infrastructures in the field of proton neutron science, EU 13 small-scale research infrastructures will be matched with large-scale research infrastructures to become dedicated partner facilities. The instrument will help overcoming the gap in research and innovation performance among the BSN countries. The today's symposium is an important milestone in implementing this tool. The second instrument is BARI. The second instrument targets young researchers. The Baltic Science Network Mobility Program for Research Internships, BARI, offers doctoral students the possibility to hire master or bachelor students from another Baltic Sea region countries for research internship financed by a BARI scholarship. Working jointly on a research project will foster personal ties between these young researchers. So far, 27 matches could be confirmed and monthly scholarships were guaranteed. 8 of these internships are already finished. and some are ongoing or will start soon. Matches cover PhD students and PhDs and students from 8 Baltic Sea region countries, including Russia. The first results show that BARI is a very effective tool to support mobility, as it allows students and PhDs to agree individually on the time frame, on the workload. The participants can flexibly react on the potential travel restrictions which we are facing at the moment. We believe that it will be a very important tool to maintain mobilities even during pandemia, and it will be also an even more important tool in a time when we start to restart our work and our science cooperation on a larger scale once the pandemic situation has improved. Lastly, BSN continues to engage in shaping the macro region on an EU level and positioning the BSR as an own interest group, with contributing to European debates, as for example, the new Interact programming process shows, or our input into the into the Horizon Europe debate has shown. We see BSN as an enabler and accelerator for science policy in the region, and we are confident that our work will influence the transnational cooperation for the years to come. We are now happy to have 12 partners and 14 associate members from ministries, universities, the university networks, and CBS as on board that are working together to foster science cooperation, to foster scientific cooperation in the Baltic Sea region. On behalf of the entire BSN network and the Hamburg Ministry of Science, Research, Equalities and District, I wish you all an inspiring and successful meeting and many more ideas and opportunities for closer cooperation. Thank you very much.
Uplifting beginnings on the role and matters of coordination and cooperation for common development. And now we are giving the floor to Hella Lood, BSN Powerhouse Project Manager, Ministry of Education and Research of Estonia. Hella, the floor is yours and good morning.
Good morning and thank you. Thank you for the organizers and thank you to Klaus for providing the wider context to the symposium and also for my own presentation. I also want to say a very warm welcome on behalf of the LaunchPad project team and on behalf of the Ministry of Education and Research of Estonia. In my presentation, I will give a more detailed insight into the concept of LaunchPad, as already referred to by Klaus, talking about what is it all about and what is it that it offers. And I would also like to acknowledge with my presentation that the symposium, the conference today, and the hackathon in the next 3 days is part of a bigger picture, actually. So the journey begins today and the LaunchPad has so much more to offer. Very shortly, again, about the aim of the LaunchPad. The following keywords are important here: photon neutron science, research infrastructures, cooperation projects. So the LaunchPad has been designed to support the launch of cooperation projects. And we are to test and evaluate the approach of 3 steps. The first step, symposium, taking place here and now, is designed to facilitate matchmaking and working on the joint cooperation ideas. It will result in draft proposals for collaboration projects. The second step forum will involve the expert panel who will review the draft proposals and select some for the coaching. And the third step, coaching, is for further support for developing the draft proposals. So the symposium is just the beginning of our journey with the LaunchPad. From the organizers' point of view, we are hoping to get your valuable feedback on the process and also some project idea drafts. However, we will not stop here. The LaunchPad can have further support for the development of the project drafts. And this further support for the development of these drafted projects will be combined with two directions. It's a combination of the feedback from the expert panel, who will serve as a certain filter for excellence or a peer consultation. And it will be combined with the concrete financial support by LaunchPad coaching for these selected projects. So there will actually be funds available for coaching activities in order to transform these drafted concepts into concrete proposals, which will give a better chance of getting access to research facilities or funding. The budget for LaunchPad coaching available is 15,000 euros with no limits per project. Just to be clear, we can give no guarantees for funding to the drafted projects or getting measurement time at the research facility. We will also not award any research grants or co-funding to research grants. What we can do is support the development of soft skills, team building, and partnership. And we have taken a very open and flexible bottom-up approach here to really allow the project teams to come in and say what is it that they really would need for the further development of the project draft. So the support will be tailor-made and negotiated for every selected project. Due to this very open and flexible bottom-up approach, it is not possible at this moment to give any final list of the activities supported, but you can find some of the examples here that would support the development of soft skills, team building, and partnership. The exact coaching activities will be negotiated and confirmed for every selected project. What will not be fitting under LaunchPad coaching is also brought out here. This is not the final list. However, I would like to emphasize that costs not connected to the drafted project activities or not contributing to the Baltic Sea region is something that we cannot support. For instance, if there will be any partners involved outside of the Baltic Sea region, it is a requirement that at least one partner should be from the Baltic Sea region. And the Baltic Sea region also must clearly benefit from this partnership. We cannot cover any staff and administration costs or costs for buying chemicals and equipment or publications. There are also some costs that cannot be covered due to the general financial rules of the Interreg. For example, the costs for the service fees or related to the foreign exchange rate, etc. So it is not a final list here. All the costs supported under the LaunchPad coaching will be negotiated and fixed case by case for every selected project. So this is actually what the LaunchPad has to offer in addition to and beyond the symposium. What we are waiting for are the short project idea drafts for collaboration. These are really project idea concepts, really, not the extensive grant proposal in a traditional sense. up to 4 pages long, describing the motivation for the proposal, the scientific or engineering background, methods, experimental and technical requirements, expected results and their impacts, and collaboration aspects. This is mainly about who are the partners involved and what is the actual role and contribution to the project of these partners. And we also ask for the preliminary action plan for further development of the project, including the indication about what kind of activities could be supported under coaching. The call for these short project idea drafts will be open right after the end of the symposium, with a deadline of November the 16th. The project idea drafts can therefore be submitted by the end of the hackathon or finalized later on and submitted by the deadline. I would also like to stress here that it is not a requirement that you have to take part in the hackathon in order to submit this project idea draft. So this opportunity will also stay open and available for the others as well. We are open to all kinds of proposals. However, the expert panel has to select some of the projects for coaching, and therefore the general evaluation criteria will be followed. And these will include scientific or engineering excellence and relevance, collaboration aspects. For instance, are there partners from different Baltic Sea region countries involved in the partnerships, or any other partner outside of the Baltic Sea region involved? Are there different fields of research involved or combined, including the areas outside of the typical fields of research, for instance, history, arts, geology, etc.? Are there different research infrastructures involved? So the more aspects covered, the higher priority will be given to the proposal. As for the wider importance and impact of the project, the relevance of to the society and wider community will be evaluated. For instance, relevance for the industry, or contribution to sustainable development, solving regional or global challenges, etc. Potential for further development of the project idea and continuation of collaboration will be evaluated based on this preliminary action plan for the further development of the project. What we would like to see is the longer term perspective for collaboration, that there is a potential for continuing cooperation and development of this project draft even after the end of the LaunchPad events or the end of the BSM Powerhouse project. And what will happen next is after the submission, there will be a meeting for the expert panel. The expert panel will review the draft proposals and meet with the project teams. They will give feedback to every draft proposal and select some for coaching. After that, coaching activities will be negotiated and confirmed for each of the selected projects, and the activities can take place within the longer period of January until May next year. And I would like to, before conclusions, say that all the necessary information about this call for draft proposals with all the necessary information will be published on the LaunchPad webpage by the end of the symposium. And to conclude, I really hope, and I would like you to find by the end of the symposium that you have widened your perspectives, get inspiration, that you have extended your network and enjoyed of being part of something innovative. And beyond that, I would wish that you used the opportunity and come with us to this journey of LaunchPad. So thank you.
Thank you very much, Hela. And two wonderful things we can take over from you. The first one is good news that the funds are available, and these days will let us much more easier to get into the funds. And secondly, of course, the journey begins today. I like this very much, this concept of journey or walking through the wonderful information we're going to have today. Yes, we are ready to start the journey, and the journey, as always, we start with the technical matters, and the technical matter is there are going to be a lot of Q&A sessions. After each speaker, there's going to be a Q&A session, and you can post your questions with the help of platform menti.com. Menti.com is the platform, and at the particular moment, you can see that on your screen. And you can register yourself in the menti.com platform with the help of QR code that you see in front of you. This wonderful QR code looks nice, looks beautiful. If you are taking your phone and putting just the camera on the QR code, it's going to recognize that, and you can go to menti.com, and that's the place where you can post the questions. If you are doing that now, and we strongly encourage you to do that right now at this particular moment, because we're going to test the system. We're going to test the system of questions and answers. So for the testing the system, there is written, what's your question? Then I'm giving the question to you. How do you feel? How do you feel today? If the QR code is not readable for you for some matters, then you can use also the code which you see down the screen, 9670848. So just register yourself in the system of menti.com, and I am now raising the question to you. How do you feel this morning? How do you feel this morning? And just write down your feelings at this particular moment, and we're going to see that the system is working well and everything happens. And I see already that the first feeling nice, good, that's fine. So just register yourself in the Menti.com with the QR code or with the good old-fashioned credentials that you see in the left lower side of the screen, and answer my question. So how do you feel this morning? Please just give some sign that you are today with us and you are online with us. Okay, and I see there is a couple of hyped, curious, wonderful, everything okay, just great and awesome and all good. Frederick, wonderful Frederick. I'm happy that you are today with us. And yes, the system is working. Curious, great, so fine. Greatness and curiousness, those are two main emotions dominating at a particular moment. And needing coffee, me too, needing coffee, always needing coffee. Online conference options are those that you can get coffee anytime and continue to watch the conference. That's wonderful. Thank you very much that you are joining in. So you can post your questions in menti.com all day long about the topic, about the content we are discussing, and also to particular speaker. But then please write particular speaker's name down and post your question for the Q&A session. Now we are ready to start our journey, the first part of the day, research infrastructure session. And we're going to start with the MAX 5 laboratory report. MAX 5 laboratory is a Sweden national large-scale research infrastructure and the world's first fourth generation synchrotron light source, providing researchers with extremely brilliant X-rays for material science. So really enormously interesting story to share from MAX 5, and I'm giving the floor to Magnus Larsson, Head of Industrial Relations of MAX 5 Laboratory, Sweden. So Magnus, good morning. How do you feel? And the floor is yours.
Good morning. Thank you very much for the introduction. Can you hear me?
We can, wonderfully.
Perfect, thank you. So just one thing about the number, it's MAX 4. We're still on the fourth generation light source. We are not yet on the number 5, but I bet our scientists are really thinking hard about what will the next generation, the fifth generation, look like. But so far it's MAX 4. And thank you much for that introduction. And let's see if I can get my slideshow working here. And okay, I hope that shows you a nice winter image of Max IV laboratory.
Mm-hmm.
So I'm head of industrial relations at Max IV, and I'm going to give you a little bit of an introduction to the field here. And as you heard here, it's the Swedish National Large-Scale Research Infrastructure, and we are publicly funded organization, different types of public fundings, also from the Swedish universities. But quite interestingly, we also have some international funding. We have Finnish Estonian investment in one beamline. We also have Danish investments, and we also have private funding from Novo Nordisk Foundation and a large funding from Knut and Alice Wallenberg Foundation. And quite interestingly, also industrial funding from the Swedish forest and paper industry that I will say a few words more about later. But I would like to take these 20 minutes to give a short introduction to Max IV and synchrotron light sources. And I will also, I will not spend so much time in the actual science, because we have a lot of good speakers later today that will give you good examples of what type of science you can do. But I will say a little bit more about how do you access these facilities, what are the access modes, how do industry access these facilities, and spend a little bit more time on that side, since I'm working at the industry office. So what is Max IV? You can simplify it as saying it's a collection of advanced analytical tools, all based on X-rays, and they're collected in this big facility. But the instruments are nothing without the people, and I think the really key thing is that we are a user facility. So we have a lot of great scientists working at the facility, providing good science, but the facility is not built for them. It's built for you, the research community. And once we're completely up and running and fully equipped, we will have more than 2,000 users passing through every year. And we have this organization set up to make sure that all these users can pass through this organization. So the dynamics is that you, as a scientist working in most cases and at a university or an institute, preparing this experiment over quite some time, and then you have a time slot for a day or a week performing your experiments, and then you go back to your institution or your company for that matter, and continue working with all the research data that you gather. And from our point of view, we have the next user that we need to support and take care of. So that we all are user facilities is really key to what we are. Just a few things about Max IV. We are located in Lund in South Sweden, and we're not alone in this part of Lund, even though it's a greenfield area here. We have our neighbor, European Spallation Source, being built, and the Science Village area in between. And if we look from the other side, it's easier to see, and it's a little bit more updated photo I see as well. So the European Spallation Source being built, Max IV here, and the city of Lund, and in 10-15 minutes away, city of Malmö, and then the bridge across to Copenhagen Airport and the city of Copenhagen. So we're located in an easy accessible area of the southern parts of Sweden. And a few things about Max IV and ESS. So Max IV, we are working with X-rays, so light as our probe to look at matter. We're a Swedish facility with a history for more than 30 years. So there was, of course, a Max 1, 2, and 3 before. And we opened up our new facility here in 2016. And X-rays interact very well with the electron cloud, you can say. And ESS, our neighbor, it's a Neutron facility. It's a spallation source that is being built. 13 European member states with hosting from Sweden and Denmark. We've been building that for quite some time, but the science is starting end of 2023. And as you will hear more about, the neutrons interact very well with the nuclei of the atom and gives a completely different picture. And in combination, you can do amazing materials science. But going back to X-rays, it's of course started with Wilhelm Röntgen getting the Nobel Prize, more or less from Nobel Prize in Physics, actually the first Nobel Prize in Physics, more or less from this photo that is supposedly his wife's hand. You can see the wedding ring, using the state-of-the-art equipment, high voltage generation, accelerating electrons onto a target and generating these invisible X-rays, hitting a sample and then a detector. And that's also how we build our facilities, but we don't want this light bulb kind of widespread X-rays. We want this really almost laser-like focused X-rays. And that's why we build the facilities the way we do. So MAX 4 is built with a linear accelerator, bringing up electrons to close the speed of light. And then we're sending them into, in our case, in 2 storage rings. And around these rings, we have these sections where we force the electrons to leave some of their energy in the form of light. And that light comes out in the tangent. And because we built these ring-shaped storage rings, we can have several of these stations operating in parallel all around these rings, providing X-rays for material science. And if we just dive into MAX 4, we have today 10 beamlines in operation. We have 6 more coming online over the coming 2 years, starting with this spring. And we have space for more. So over the 10 years, over the coming years, we will increase with 10 more beamlines. And if we just want to say something really roughly, what type of experiments that can take place at the Synchrotron Light Facility, we have different type of spectroscopical techniques where you can get chemical, electrical, and magnetical information from your sample. We have different scattering techniques where you can get structural information all the way from atomic structure up to through nano regime up to microstructures. And then you can combine different type of signals and get all these different imaging techniques based on the signals you get out, also tomographic imaging. And I believe we will see some good examples of what type of science that we can get out of this later on. So I would like to say something about the different access modes. How do you get access to these type of facilities? And starting with the most common access mode, which is the open peer review access or general access, where we have at MAX 4, we have open calls twice per year. You can look at our website, and there are these websites where you can find when are the open calls, for example, Way for Light or light sources. And I believe the Neutrons facilities also have these websites where you can find more information. Otherwise, you can just come to the website of your facility. You send in an application to write a proposal describing the scientific gains that you hope of this experiment and how you will perform this experiment. And then we have an independent international panel ranking these proposals on scientific merit. And we will get this ranking back, and we will award beam time to all the proposals, starting from the top all the way until we don't have more beam time that proposal round. And this beam time is for free, and the way you pay back to society is that you publish your results in the end. You don't publish immediately, but of course you work with your data, and over the coming years you publish your results. Working with industry, We also have another access mode, we call proprietary access, where you can get access in a different route if you're coming from a company. And here we have a little bit shorter term and faster access. So we have these set up regular slots over the year where you can get beam time, or you can set up a framework agreement and have regular access over a long time. And this access is within a confidentiality agreement, and we charge fees for beam time and services, and all the results belong to you as a company, and you do not need to publish anything. And these are sort of the two main access routes that we're working with at Max 4. But I would like to say a little bit about before you come to the facility, there are things, of course, you need to think through, and it goes for everyone, but in particular for industrial users, that you also need to consider in your when you're performing going to perform your experiment. So this is a bit of a puzzle. You have a challenge of some sort, and you would like to move on with a solution, or you would like to test your hypothesis, and you know that the method is somewhere at the through an experiment at a facility like this. But of course, before you come here, you need to transform that question into an experiment and finding the right method. Sometimes you also need to develop a new experimental environment. Maybe you need to rotate your sample and pull at it at the liquid nitrogen temperature at the same time. And that is something that is maybe not available at the place where you want to perform your experiment. And on the other end, after your experiment, you end up with sometimes a lot of data, and you need to work with your data, a lot of analysis and modeling. And these two pieces of the puzzle is something that you really need to take into account and consider, and they're also quite labor-intense part of your experiment. So a good way to approach one of these facilities is to do that together with someone who has this experience, who can help you with the way before and also the time after. And now I would like to say something that is especially for industry, and how you as a company can come and use the facility. And there are different routes into Max 4. We have some companies, we call them advanced users, companies that have the in-house know-how of how to use the techniques at the facility, and they can just come directly to facility, buy beam time, and take care of the data and do the analysis themselves. And some of them are even using the open access route and publishing the results later on. But most companies are not in that situation. They need some sort of support, and there are a number of support organizations to give you some what we call mediated access. There are research institutes, there are mediator companies, and there are projects like Links project that we'll hear more about later today that can support companies with their access. We also have some support at the facility and the industry office. You can contact us. But really the big access mode is to come with an academic collaboration. So industry in academic collaboration applying for beam time, and that is really a good way to start getting access to these tools for companies. And there's also last, or maybe not last, but there's one alternative that you can make an investment. And this is something that I would just like to say a few words about. The Swedish forest industry that made a strategic investment into Max 4 and built one of their beam lines of their own. So the forest industry, together with, I can show this slide instead, several Swedish universities, big companies, the research institutes have gone together and backed through both the Innovation Agency and most notably Knut and Alice Wallenberg Foundation to build and operate this type of dedicated beamline at MAX IV to really match the needs of that industry segment. And TreeSearch is this large research platform, and within that they have research infrastructure and infrastructure investments such as this one. And this sort of triggered us to start to work with industry in this clustered way where academia, institute, industry are working together and reaching out to these facilities. And we are working on a setup for the metal industry. We call metal beams, running workshops and symposia and helping and supporting the industry to get access to these facilities. And we also launched a program for the food and packaging industry called Northern Lights on Food that are now applying for funding to set up a research center. And this is a Nordic center that's being set up, but aiming to a larger European reach out. And at the industry office, we have, together with MAX IV and ESS, together with Science Village and RISE Institute, set up a website now called MAXS Industry Arena, available at maxs.se, where companies can find their collaboration partner and resources to get an easier access to these facilities in different ways. And I would like to round off there and conclude that these facilities are open for you to use. And I would like to join in with Hella's recommendation to take this opportunity now and use this week of networking and getting connected to researchers and start to approach and start figuring out how to use these facilities for your research and development. And also, if you're from a company and you would like to have confidential access, then you just reach out to the industry offices at these facilities. And with that, I would like to say thank you.
Thank you, Magnus, very much. And I'm totally happy that I upgraded MAX IV to MAX V at the beginning. So it's just looking into the future. Yes. We have a couple of questions, in fact, and one of the questions is, what is the waiting list if you want to approach a laboratory? So how busy it is, taking into considerations this peer review access and also the private access?
Yeah, so all these facilities are always full. There's always more users than facilities, but we have this dynamic so that you can apply twice per year. So we have this 6 months between each application for the open access, and then there's the reviewing time, and then you will get your time. So between 6 and 9 months usually from your application time. When it comes to proprietary access, paid access, it depends on what beamline, but usually within a month you will be able to get access, and it can be even faster than that. But usually there are the practicalities that takes a bit longer. We have the standard agreements that ready to sign, but maybe your legal department would like to go through it, and then it still takes a little bit of time. So we run that in parallel, but within a month.
Within a month. We have also a question from industry considering those practicalities, and the question is, what is the approximate hourly cost of the proprietary access to the different beamlines?
So they're about between, say, 550 and 800 euro per hour, if you talk about the European facilities. And in MAX IV in specific, it's 6,500 Swedish krona per hour, which is roughly 650 euro per hour.
Thank you very much. And then we have the third question about cooperation in between laboratory and Latvia, Lithuania, Estonia. How could you evaluate this kind of experience until this?
I mean, it's an intense collaboration. I think we even had an Estonian director. We have a strong collaboration between the countries, but me personally, I know a bit too little to rate that in any way.
That was an elegant way to answer that, knowing a bit too little. Thank you. Thank you very much, Magnus, for your presentation, and definitely all of those who are watching this conference, you can also, if you want to get in touch, you can write in the menti.com the question, how can I get in touch with particular laboratory and particular presenter? So feel free, this conference symposium is made for extending the contacts and network. So find the courage to do that. That's the main idea on this. Okay, we continue, and our next point in the journey is European XFEL or XFEL. And European XFEL is an international non-profit company located in the Hamburg area in Germany that is owned by 12 European countries. And the European XFEL operates, maintains and upgrades 3.4 long X-ray laser, kilometers long X-ray laser, which produces flashes of X-rays of unique quality for studies in physics, chemistry, materials research, and the life sciences. And now it's my pleasure to give the floor to Christian Bressler, Professor of Physics, leading scientist, European XFEL from Germany. Christian, do you hear us well, and are you in connection with us?
Yes, hello. Good morning, everyone, and thank you for the introduction of European XFEL. I guess I'm ready to present. If my slide is visible now, is it? Oh, fine. Excellent. Then, welcome to European XFEL in Hamburg. It's the latest newly built X-ray free electron laser facility on this planet, and I wanted to walk you a little bit through what it's all about. It started 3 years ago and with 6 specialized experimental stations, and is now ramping up to get into full power X-rays for research opportunities. To give you a little bit of broader context, European XFEL is not the only one on this planet. There are a few more free electron lasers. First, the groundbreaking linear coherent light source, or as we call it, LCLS, which was inaugurated 10 years ago, originating from the older SLAC accelerator machine. And has more or less pioneered the research opportunities we all now are building on and trying to expand further into the future. Shortly after, in Japan, next to Spring 8 synchrotron, there is the SACLA free electron laser, which is also now in full swing and operational. And just around the time or right before European XFEL inaugurated first beam, well, the Swiss FEL went more or less online, and the Korean X-ray free electron laser went online. LCLS, which is more or less the pioneer in this field, is now entering phase 2. So they are now inaugurating, as I speak, LCLS2, which will provide even more advanced conditions, almost similar to what I will present you today as well. European XFEL is a huge installation in the greater Hamburg northwestern corner. On this aerial photo you see on the bottom right, the DESY campus, which has the PETRA-S synchrotron, of which we'll hear right after this talk, and also the enabling, there's a little Linux structure in the northeastern corner called Flash. That's the femtosecond laser at Hamburg. It's enabled the technology that was then expanded up to 3 kilometers here for European XFEL, namely this superconducting LINAC technology, which allows us to accelerate many more electron bunches than anywhere else on this planet. And then we run into a maze of tunnels, 5 of them we have, of which 3 are received by what we call scientific instruments. These are the experimental stations where you can, as a user, eventually do your experiments once you went through the application process, as pretty much as Magnus outlined earlier. It is, as of today, the strongest X-ray beam on this planet, meaning that we can allow 30,000 of these raw X-ray pulses to enter the experiment, while all the others are more or less limited to 100 pulses per second. So it's almost 100 times more intense than all other free electron lasers combined. It's based on self-amplified spontaneous emission. This is a process where an electron bunch travels through a radiation generating device we call undulator. And these are just alternating magnetic fields, which in the Lorentz view of the electron frame are extremely short, and there are some tricks, and you eventually turn this sinusoidal function into a very short undulation on the order of 1 angstrom, which is the X-rays we eventually take out of that. These are accelerated and self-amplified over a fairly, well, you could say short or large distance of 100 meters is the order of magnitude, in order to then generate what we call microbunches. I won't torture you now with the details about this, and this is then the moment when we run into what we call saturation. Gives you at the end pulse energies very comparable to what you have from commercial amplified laser systems. So it's on the millijoule level, up to 10 millijoules possible, or if you prefer 10 to the 12 photons per pulse. What comes from this process, the process of generating the radiation is a stochastic process. It starts with spontaneous emission. That's on the far left corner. Somewhere here is the first photon that is spontaneously emitted in the correct direction. And that is then amplified all the way out. This leads then to some indetermination of the process itself. And that means we get first of all, we get here's a simulation of the time structure where you have many short spikes. These more or less originate from the microbunching. But even if I would measure the spectrum that you get out of this laser, you would also see a similarly spiky spectrum. Although it is highly monochromatic, it's not precision monochromatic. For that, we have additional schemes to further monochromatize the radiation. But at the moment, it's stable down to, it's monochromatized to 0.1%, which is already pretty monochromatic for the X-ray range. What comes as a difference to, let's say, the PETRA-synchrotron you hear about in a moment, and this linear accelerator is not only the pulse structure, which is more limited to 100 picoseconds at a synchrotron, with about, let's say, 10 to the 9 photons or a microjoule per pulse, but you can squeeze everything into the femtosecond time domain. And you squeeze in a lot of photons, 10 to the 12, 10 to the 13, and maybe a little bit more is possible. This is now completely different X-radiation than I worked with almost my whole scientific career with synchrotrons, because we can do things now with X-rays that we couldn't believe possible. And here you see a 5 centimeter slab of stainless steel after 30 seconds with the X-ray beam going focused into it, you can see the exit hole where the beam comes out, and it drilled its way all the way through. And we meanwhile also managed to go through 30 centimeter thick copper slabs. So it is a powerful, dangerous beam, but it is also very bright. And if you have interest to measure something that is very subtle or very weak effects, you can do this with this X-ray beam. The experiments we do are typically done in a, let's say, radically different fashion. It's called more or less diffract before destroy. So this is now the popular way of doing protein crystallography. Namely, you don't put in a single crystal as at the synchrotron, but you have here in the fluid many micro, nano-sized, nanometer, 100 nanometer sized microcrystals. And each pulse from the X-ray, so these combs are similarly are indicating the individual X-ray pulses we put through the sample. You can then record for each pulse a diffraction pattern from a single nanocrystal. After this measurement, the crystal blows up and is gone, and you can no longer use it. That's why you need then such an arrangement to repeat the measurement to get more signal quality by flashing new, fresh nanocrystals through. And that's how you can then get high quality diffraction images coming out. This is now too technical, but I just want to highlight that wherever the sun is shining, that's where it's orange is where the light is. And so this is now the view of the 3 tunnels that we have occupied right now with certain X-ray energies. We have 1 branch for soft X radiation and 2 branches for hard X radiation. And each is feeding 2 specialized experimental setups for which the goal was to design them such that we can cover the broadest range possible of experiments that can be done. And therefore we have these funny 3-letter abbreviations, and there are always 2 instruments, and here also 2 available for scientific research. Accelerator is now in good shape and is now ramping up to the highest energies, meaning that we can get 20,000 electron volts or up to 20 kilo electron volts X-ray photon energies. And this is a first that was achieved. And right now, this from last year, values are below a millijoule. Now we can go reliably up to 2 to 4 millijoules of pulse intensity. This is now a little bit a zoom into the maze of electron tunnels. So if you look at this figure, the accelerator here on the left part is 2 kilometers long, and you don't see it. And at the end of it, we have the switch yard where the electrons are sent to 1 undulator, or they go straight to a second undulator, bent around the corner and going to a 3rd one in series. This allows us then to feed these 6 scientific instruments, as we call it, and I will present them in a moment. And you have here 2 further tunnels that are not yet equipped, but we had already started workshops with the interested user community, and we will continue this to define the needs of the community in order to make the best use of these 2 new radiation tunnels, with which we can do even further experiments. And this is still coming up. These are the 6 instruments in user operation. They were not turned on all at once, but we had them ramped from 1 tunnel to the next. So we started here on the left and moved slowly over to the right. These instruments all use X-rays, all are equipped with lasers to do time-resolved investigations down to the femtosecond time scale. So this is the similarity of all of the 6 instruments, and energies are ranging from the very soft X-rays, what we call is the carbon K edge, around 250 electron volts, all the way up to now starting with 20 kilo electron volts. In order to get access to these facilities, you have to have a scientific idea and discuss these, and this can be developed also with the people in charge of these instruments, of each of these instruments. So if you get in touch with them, they surely will listen to you, and then they will say either maybe you should go to Adrian and not to me, so somewhere else to discuss the idea, or they would give you some advice how to move on. And this I can only advise to do, talking to people, especially as Magnus pointed out before, talk to previous users, because they know best the language and the understanding of and have a better understanding of the instruments that exist. Here is now a short compilation of what instruments we have and what kind of scientific fields they cover. I don't think I want to torture you too much now with each single capability. I just want to mention that these experiments are involved. We have many, many pulses per second, many tens of thousands, up to 30,000 or so. And we have developed within at European XFEL detectors that are capable to record a full image for every single shot. And this gives a data amount that is going through the roof. And we are dealing with this now, how to provide this vast information to the users so that data analysis and interpretation of the experiments can be done in a more smooth way. You don't have to know everything about how we record data and analyze them. Well, analyze you should know, but many details we can take over for you. So you should more or less concentrate on what you really want to measure and how you want to measure it. And depending on what kind of experiments this is, there are easier possibilities if you go to this instrument and not to that one. And this is where we can help, certainly. And as Magnus pointed out, previous users can also give very good advice how to approach these new opportunities. I'll just give you one scientific example that is more closer to my own heart. This was a last year experiment by one of the users from a university in Germany, Paderborn. And there they were aiming to observe in this bi-metallic complex. So here we have an iron-centered complex, a bridge, and a cobalt-centered complex. And the reaction was aiming to observe the departure of an electron triggered by sunlight or by a laser, in this case, going onto the ligand system, transferring over to the cobalt system, and arriving eventually onto the, and reducing the cobalt ion itself. This is important because afterwards, when this is being reduced, this chlorine atom can move out and you can attach water, split water, and this could be indeed a seed for a photocatalytic converter. And the goal of this experiment was to indeed observe that the departure time and departure dynamics, how long does it take for the electron to move over? And for this purpose, now the instrument called FXE, femtosecond X-ray experiments, was able to record both the iron signal, so the departure signal, and the arrival signal on the cobalt center. And this is pretty cool if you can have both signals at once, and you can see how something moves and nothing happens on the other side, and then it arrives, and you can monitor this. These are experiments that we can now do on the sub-picosecond down to 100 femtoseconds and partially below timescale. With this, just trigger your mind how what exactly you would like to study, and we can help on the wildest ideas and hopefully find a suitable instrument. Publications are coming out because the facility is now overcoming the bug fixing stage, and now new experiments from users are now moving out from the different scientific instruments. So this is where we would hope one of your publications would come out as well. And this brings me to my final topic that I want to present to you. How can you take part in these activities? Apart from the current initiative, do come to our users meeting. It's going to be an online event in January, end of January next year. And it is a very big event and traditionally highly visited in pre-corona times by scientists from all over Europe and the world, and Germany as well, and focusing on European XFEL and the synchrotron DESY. There are specialized workshops you can visit. You can think of a sabbatical at European XFEL, or even about joint PhD positions if the scientific interests are found. Before you write a proposal, just like Magnus said, keep in mind you have to justify the use of a free electron laser. That is the many photons we have. It's ultra short and it's highly coherent. Then you can contact people you know, or instrument scientists, or myself. You can discuss your idea with any instrument scientist. And you can actually also initially join a community proposal. These are collaborations of many institutes joining forces to do one single experiment in order to bring forward the field they are interested in. And you can also use one of our bio laboratories. We have several large surface of biolabs. And then you write the proposal. And the proposal review panel is consisting of external experts. Keep in mind, rejection rates are rather high, they're not too low. And also keep in mind, European XFEL is a lot more than 6 instruments. It has many, many groups and labs that you can use also equally for your research. So you're not only limited to using the X-ray beam or so. So we would hope that you would become one day happy users, as we already had last year, and hopefully again when Corona times are over. And with this, I thank you very much for your attention.
Thank you very much, Christian. And we have a couple of questions for your very well-framed and excellent presentation. One of the questions is, what is the practical advantage of using FEL rather than synchrotron light sources for industrial measurements?
Sure. This I would probably pass to our industrial expert, but I would say, put it this way: if there's anything you want to study which provides faint signals, where you need lots of flux, then a free electron laser might be the instrument of choice. Keep in mind the industrial interest that you should have one of these, and the second line here where the mouse is, many photons. This is something we have in a single pulse that no synchrotron has. It is ultra short, femtosecond short, so you can observe wave packet dynamics, which otherwise you couldn't, and it's highly coherent. So if your industrial application requires information on either of these, which require either of these 3 properties, these are the 3 pillars of FEL excellence or so, then you would not go to the synchrotron for these experiments.
Okay, thank you very much. What is used for the beam stop for this extremely destructive beam you showed?
I didn't understand. What is used for
the beam stop for this?
Yes.
Yeah.
Yes, that is an important question that also excites our safety group, our radiation safety group, a lot. But the answer is the following: you don't focus. If you have focus beam of about 10 microns up to 20 microns, then you drill through everything. There is no beam stop available. If you have several meters, usually we focus the beam on the sample and then it expands outwards. As soon as the X-ray beam is larger than, say, 500 micrometers, then you do not drill through any material anymore, and you can stop it with the usual safety precautions as you have at a synchrotron. But the safety group is very much alert that we never ever come into conditions where we could focus onto the what we call Hutch walls. Then you can run into big trouble. And usually we make sure we have several up to 10 meters of air between these conditions and the wall, so that the air can take away light as well. And we saw that this is indeed possible to block the beam.
Okay, thank you. How many people come at the XFEL DESY users meeting?
Yes, this is not totally clear because many people come to both meetings, the DESY user meeting with Flash and Petra and European XFEL. But we had, for all three facilities, we had last year, I think, over 1,000 people visiting, which is unique worldwide. And for European XFEL, the registrations were on a few hundred level, I think over 400 last year. So this is a superb, in pre-corona times at least, or post, superb opportunity to talk to various scientists and from all different directions, institutes, and so forth. And I hope we will be able to put up a similar program that allows such exchange this January.
Okay, and the final question that goes to you, you mentioned a couple of times that good practice is to reach up to previous users if you want also to do some connections with the laboratory. Do you offer the list of previous users? That was the question. How to contact them?
Yeah, I guess you should know them probably beforehand. The list is vast. We don't collect the list such that we pass it out, but for example, in the afternoon, you will hear from one of these users who is, I think, the last talk in the afternoon. He will present possibilities, but if you get in contact with me and say in which field you would like to investigate, I can either immediately provide such information or pass on to people who would know better which one to contact best. It's not a secret, but it's we just have very many users actually.
Okay, thank you, Christian, very much, and also for showing the clear way, clear path, how to move forward if there is such an interest and initiative. Thank you very much. Now we are switching over to the next presentation that we have, and DESY. DESY is one of the world's leading accelerator centers. Researchers use the large-scale facilities at DESY to explore the microcosm in its all variety you can imagine, from the interactions of tiny elementary particles and the behavior of new types of nanomaterials to biomolecular processes that are essential to life. So all spectrum you can imagine. So my pleasure to give the floor to Hans Christian Wille, group leader of FS-PETRA-S experiments, Deutsches Elektronen-Synchrotron, DESY, Germany. So the floor is yours, Hans. You should switch on microphone or something like that because you're extremely silent.
My microphone is on. Can you hear me?
Okay, everything's fine now. Some
Okay,
kind of glitch in the system.
Okay,
yes,
thank you very much. Also to the organizers to give me the opportunity to give you a little overview about what we are doing, especially at the PETRA-Synchrotron at DESY. It's, as you have already heard, the DESY campus is rather large and accelerator campus with a long history, and we're actually having quite some experience in building accelerator facilities, and we are sharing the campus with many cooperation partners On site, as you already heard, we are starting to accelerate the electrons for the European XFEL. We have our flash laser, the soft X-ray laser on site. And of course, one of our working horses is the FS-PETRA-S synchrotron radiation source, which you can see here indicated in blue. Many people are contributing to this, and also stakeholders, shareholders with own beam lines. I should mention the cooperations with the University of Hamburg, the Max Planck Society, the European Molecular Biology Laboratory, and the Helmholtz-Zentrum Geesthacht. And also we have a few partners, international partners like Sweden, India, and Russia, who are invested in our initiatives. So this is the outro of my talk. I'm just going to briefly show you a little bit about the features and scientific scope of FS-PETRA-S and also FS-PETRA-4, our future source. I will give a few research examples also, and then have an outlook to our project FS-PETRA-4 in the end. So here's the fact sheet about FS-PETRA-S. This is actually a rather old synchrotron already, or accelerator at that time. It was already built in 1978, but at that time for high energy physics, and it was also very successful in the first detection of the gluon, for example. It was then used to pre-accelerate protons and electrons for our largest ring, the Hera, which is already shut down again now. And after the shutdown, this was the opportunity was there to use this ring and rebuild it as a synchrotron radiation source. This has been done starting in 2007, and we started user operation in 2010. The energy is 6 GeV, so it's a high energy storage ring. We provide for the third generation source a really good emittance values. The circumference is one of the reasons for this. It's a large ring, it's 2.3 kilometers in circumference. We are covering a large X-ray energy range. And at the moment, we have 23 beamlines in operation. So we have 23 beamlines, as I said. They are now distributed over 3 halls. The largest hall here is the Max von Laue hall, where we host actually 15 beamlines with variable techniques. And we have 2 smaller hutches that have been built a little bit later, which we call the extension project. And there are another 10 beamlines, most of them already working. So the methods at the beamline are very diverse. We are doing scattering, diffraction, spectroscopy, imaging, and coherent applications also, and they are specialized in several parameters. And I should also mention, of course, that we have external contributions. We have 3 beamlines run by the EMBL, 2.5 beamlines by the Helmholtz-Zentrum Geesthacht, and we have an Indian virtual beamline. This means that they have a priority access for about 1.3 beamlines. And we have actually a dedicated Swedish material science beamline, and the Swedish community actually gets about 1.9 beamline equivalents in total. Some statistics in the beginning. So this is the statistics from last year, because as you can imagine, this year was a bit hampered by the COVID-19 crisis. So this is the more kind of a standard year that I'm showing you today. 2019, we had 3,150 unique users, about 6,300 user visits. And as you can see, most of the people are coming actually from Germany. Most than half of the users are coming from Germany, but we have considerable contributions from other countries as well, especially also here, Denmark and Sweden, as you can see. I should mention that this portion usually is higher due to our contract with India, but we had a few issues last year. That's why it has been reduced. This is rather in the 5% range also. Publications also are going up. So we still have people publishing from Doris. And about Doris, was the older synchrotron source, was shut down in 2012. And then we have had a little, for the extension, we had a little break here. That's why the numbers are so low. But then, as you can see, we are steadily going up with publications and users. I'm sorry. I want to just, of course, in this round, I also would like to show you a little bit about the statistic for the Baltic Sea region. So in 2019, we had 593 unique users coming from that region, and you can see the distribution over the different countries here. And a really large part from Sweden is, of course, also due to the fact that the Swedish Research Council is a strategic partner for us and is operating the Swedish Material Science Beamline. We have quite some networking going on in the Baltic Sea region. I would like to mention a few of them. Here is the Baltic Science Network, LEAPS, HALOS, Kremlin Plus, Calypso Plus, Röntgen Angstrom Cluster, Carrots, Baltic Tram, and I apologize for having missed maybe a few of them. We have, of course, also in the region here, many research institutes and universities that we are working together with. Of course, also in Germany, but here I would like to just highlight the international partners from the region, which you can see from, for example, the Aarhus University, Russian Institutes for Accelerator Technology, of course, the KTH in Stockholm, the Swedish Research Council, as I said already. We have cooperations with Lund University, Max 4, and of course, many more. So let me just have a few words on the P21 beamline, because this is something really special, because it has been funded by the Swedish cooperation partners, and it is basically now operational. I would just like to give you a small update. So we have in principle 3 end stations, 2 inline and 1 side station, where the side station has these parameters, and the techniques here is wide angle X-ray scattering and paired distribution function techniques. And we have more or less empty or available space in EH2, where we can really roll in experiments and equipment instruments that you would like to use. And it's also for very bulky sample environments. And then we have this again, a specialized hutch, which is the third one, which is a diffraction setup with a specialized high energy monochromator. And you can go to time resolution down to milliseconds, and we can use wide angle and small angle scattering and imaging techniques. This is just 2 pictures that shows you that the hutches are really equipped and are in running mode. I don't want to go too much into the details here. But would rather like to show you a few science examples, because of course, PETRA-3 is doing science in many, many areas. We are going from extreme states of matter to quantum condensed matter, magnetism, superconductivity, materials and processes for energy and transport, nanoscience, information technologies, and of course also a big part is soft matter, health and life science, especially nowadays. I will come back to that in a minute. So here's as I was talking about our cooperation partners, I just like to give 2 examples from the Baltic area. So we have an experiment here led by the KTH in Stockholm about hydrogen infusion in duplex stainless steel. And this was carried out actually at P21. And here they were studying the cathodic hydrogen charging under constant tensile load. And they had the beam coming, recording the scattering under load, and they could then really make a nice depth profile of the lattice spacing. And it has been published recently. This is what they see basically. 20 micrometer depth increments, 1 millimeter translation, scanning procedure, and about 6 minutes per depth scan. A second example is another thing that is led by KTH, by Daniel Söderberg. It's about cellulose-based materials with higher strength fibers. So what you can see here is actually that they were able to design and to build fibers which are really extraordinary strengths. So best strength and stiffness combined with a stiffness to density ratio. So really going to the right corner here. And they could then study these fibers, why they were really producing them in situ at the spinning stage. And what they could really see is then that they could really study the order parameter dependent on the position of these filaments. They could really see how nicely these filaments start to align in the flow process in the fluid. And then I would like to come to a few research, actually 2 research highlights about corona, which we actually, I should mention that at PETRA-3, we only had a rather short shutdown at the end of April, or at the beginning of April, and then after about 2 weeks, we already opened again our instruments for corona-related research after we went back in a kind of reduced user service in May. So actually, there was one group coming from the University of Göttingen and other institutions, and they were studying the 3D visual pathohistology of lung tissue from COVID-19 patients. And what they could really see is that around the alveolus, there is a hyaline membrane build, which really causes that these patients suffer from a missing an O2 and CO2 exchange. So these kinds of membranes are the reason why they the exchange of O2 and CO2 is prevented. And this could really be done with a kind of tomography technique at the beamline P10 at PETRA-3, and they could study diameters of 1 millimeter with the resolution of about 170 nanometer. And the second example I would like to mention is a group that studied many proteins, biological molecules that should have the capacity to block a connection point of the virus to the cell. And actually they were studying almost 7,700 different molecules, and they could have in the end, I think, even more than 38 hits where they could show that these molecules would have the possibility to block the active sites. This was a really very much automatized experiment at P11 using the technique of crystallography. And this is also already published. Let me now come to the PETRA-4 project. As of course you can imagine, this is a really huge and large project that we are planning since some time, and we are just now in the phase of the technical design. And the basic goal of this is, of course, that we want to provide insight and help in science related to the Sustainable Development Goals, of course, that are defined. And we actually can just really do that for many of these goals. We are participating in the regions of health, earth and environment, energy, transport, and information technology with our various techniques. And the good thing with PETRA-4, or the new thing with PETRA-4, is that we will be able to really look at all length scales and really start to create and design multifunctional materials which are really tailored local structures and can basically be built and designed atom by atom and can be studied also with this resolution. And of course, we are aiming for high resolution, spatial resolution, also time resolution as good as possible. And we are also doing studies in vivo, in operando, and with highest resolution. So how do we do that? We would like to upgrade our ring to a fourth generation source, which has already been done for other sources. Of course, MAX4 is the very good example for this. We already heard about that. So the situation at PETRA-3 is still that we have a rather extended beam in the horizontal, and already not so bad focused beam in the vertical. But of course, we would like also to go to the situation that we have rather a point source with really exceeded source size and divergence values, where we really have the emittance increased by a factor of 100. And these are the numbers. If you are interested in, I don't compare them to the other sources, but I think this is really nice values, and we have a huge amount of coherence, and up to 10 keV, the beam will be actually fully coherent. So what we have at hand then is that we have really an X-ray microscope for chemical, biological, and physical processes. We can really zoom in to all relevant length scales. We can study chemical, structural, electronic, and magnetic properties of individual nano-objects in the macroscopic context. And the dynamics, we can go down at least to the nanosecond scale. So it's a complementary technique, of course, to the XFEL lasers, where you are actually, of course, much faster, as we heard before. So if you look to the difference, to the numbers, what you can see, the value that is always given is the brilliance, the photons per in a certain angle and in a certain bandwidth. We are expecting to go up about a factor of 500 in this value in the region around 10 keV and about a factor 1,000 in the higher energy region. So this means we will have a coherent fraction of the beam at 100 keV that we have now at 10 keV. And as I said, at 10 keV, we are basically fully coherent. And this, of course, gives new opportunities in many fields of science, which were experiments which were on the edge or were not feasible before are now within the range of being realized. So what could this be? For example, you do nanoprobes, you use the focus nearly full flux in the nano beam. You can basically go from images to movies. You will have a larger field of view. You can go a larger field of view, but at the same time, you can solve the needle in the haystack problem. You can really go down to nanometer resolution, especially for coherent imaging. It's very important because the coherent part gives you 4 to 5 orders of magnitude higher coherence flux density. And all these techniques that are spectroscopic and need a lot of flux and are very flux hungry, where you only get a few photons out nowadays, with having 10 to the 13 photons arriving at the sample, they can now also go nano. You can focus your beam basically with the entire intensity. And then these techniques like inelastic X-ray scattering, nuclear resonance scattering, and resonant magnetic scattering can now go to the nanoscale. And also the high energy fraction, of course, is important. You can do things that you couldn't do before because you get more flux and more coherent flux in this energy range. So the spatial resolution, for example, of coherent imaging, you can go down to resolutions below 1 nanometer. Let me give you also an example here. You might want to study cellular complexes in infection research. So you can really go down to visualize the cell structure in very, very high resolution. And you can also, for example, study the distribution of different elements with nanometer resolution. The second thing is, for example, energy materials, where you usually have applications like batteries, fuel cells, catalysts that you would like to study in operando, for example, and under charge or discharge conditions. And you can not only do that using imaging now, but you can also use now spectroscopy techniques to really see the difference in the electronic structure by using X-rays, which of course have the advantage, or high energy X-rays, which have the advantage to penetrate materials while they are working. So to look inside a battery is very difficult with visible or low energy light, of course. The project timeline for PETRA-4 is we are somewhere here. So we already finished the CDR phase. The CDR report is ready. You can get a copy, just let us know, no problem. You can also download it from our websites. We are now in the PETRA-4 TDR phase. And actually this phase goes at least up to 2022, end of 2022, where we then would like to start the project phase. And if everything goes fine, we would like to start PETRA-4 operation in 2027. These timescales, of course, have not yet been adapted to all the things related to the COVID-19 crisis. But at the moment, we are still planning in this way. So what is the beamline, or the next step? What we are doing now is to define the beamline portfolio. And this is, of course, one of the work packages for the TDR, where we really would like to get all the experts together and all the ideas, especially together, and develop a new beamline portfolio, which will consist about 30 beamlines. And of course, the important parameters are the science drivers for PETRA-4 that we are collecting. We will also take into account the resulting experimental requirements, boundary conditions from the new machine, and of course the existing beamline portfolio. And in the end, what PETRA-4 should look like is that we keep our 3 halls that we already have here, down here, and we will have a huge, large hall, an opposite position to the Max von Laue hall on the other side of the ring, where we can host another 14 beamlines, or even up to 16. And what we are doing now is actually, we are in this phase, we are preparing and collecting the scientific instrument proposals. And this call is open, and it is the deadline for this is the 1st of December. We are collecting that from facilities and users, and basically everybody who has a brilliant idea how to use the new opportunities that PETRA-4 can hand in such a scientific instrument proposal. And we also have user workshops defining the experimental requirements on different aspects. I will come back to this later. And actually, these workshops just started and they are about to run. And here they are. So we just had the first one, and we are going to have the next one on soft matter on the 28th of October. And you see that there's another one for earth and volatile material nanoscience in November, and then finally one on the technical challenges and scientific computing. So basically, if you are interested, and we are of course very open, and we need your input. So please use this opportunity, take the chance to make your science ideas part of the scientific instrument proposals. As I said, the deadline is the 1st of December. And all I can say is that we should keep working together. And I thank you very much for your attention. And also thanks to the PETRA staff and the city of Hamburg. And this is the view of PETRA-3 and the new project of the Science City Hamburg-Bahrenfeld, the newest and latest project of the Hamburg city, where we hope to be one of important parts. Thank you very much.
Thank you. Thank you very much, Hans Christian. And we have a couple of questions. The first one is, how do I get access to P21 as non-Swede? And maybe we can open this question a bit more up. Could you give overall comment on access and applications in your facilities?
Yes, of course. I should have mentioned this. Yes. So it is pretty much the same as at Max 4 or other synchrotron radiation sources. We have, of course, the absolute majority and main part of our user program is given by a peer review access. So anybody in the world can write a proposal that will be peer reviewed by external experts, and then it will be given a ranking, and depending on the overbooking and the quality of your proposal, you will get beam time. So it is absolutely not necessary to be part of any of our priority access partners. This is only a very small fraction. And of course, we have the possibility also to give beam time to industrial users, where the industrial users, the same as at Max 4, they basically pay for the beam time and they're not obliged to publish the results in the end.
Thank you. We have interesting question considering timeline. What can I do at Flash and Petra next year, or do I have to wait for PETRA-4?
You can do many things at PETRA-3 and at Flash actually, and you don't have to wait for PETRA-4. But of course, there are a few cases where you might have to wait, and if you have an idea for an experiment that you cannot already do at these sources, please get in touch with us and maybe also hand in a scientific instrument proposal. So the machines are running. We are in user service. We have many opportunities. If you'd like to know more, just please get in touch with us. Of course, you can do anything, many things already.
Many things already. We have a question considering COVID-19. Are there any kind of limitations at a particular moment that especially you have to think considering application and access in Petra?
Well, we of course have adapted our user service and our user also the access a little bit to the situation. So we, of course, following a strict every and all official corona-related measures given from, of course, indicated by the government, and we are having even stronger safety rules on site. One of the things that has changed for the users, for example, is that they, starting actually from today on, have to provide a negative corona test. And the usual experiments are restricted to 3 external users. So if you have an experiment that needs more than 3 external users coming to our campus, you really have to ask for it in advance and you need to get a permission. Otherwise, the usual rules adapt, of course. So we're keeping distance, we're wearing masks, and we're trying to operate as safe as possible. And so far, there is no official shutdown. The numbers are increasing. We are watching this on a daily basis, and we are, of course, informing our users about changes of the rules immediately. But at the moment, the only real big difference is, of course, besides following all the usual corona rules, is that you cannot come to the experiment with more than 3 people in general.
Mm-hmm. Thank you very much, Hans Christian from DESY, Germany. Have a nice day. And we are switching over to our next presentation. Before that, there was an overall question. Will the talks be available on the website or LaunchPad? Yes, they will. Shortly after the end of this conference, all the talks will be available. You will be able to rewatch them and find the information, again, what you need for your development and cooperation needs. So definitely they will be available. Now we are changing a bit our geography, and from Germany switching over to France. Institut LAUE-LANGEVIN, or ILL, is a service facility. Its purpose is to provide the international scientific community with, first one, the brightest possible beams of neutrons, the state-of-the-art of scientific instruments, and the expertise of its scientists, engineers, and technicians. And most of its neutron beams are used in ILL to probe materials, and the fields of investigation range from technology applications to biology and health. So my pleasure is to give the floor to Giovanna Fragneto, professor in ILL. Giovanna, the floor is yours.
Thank you very much. Thank you for the invitation. Thank you for the introduction. So as we said, well, we are not only moving country, we are also moving to another kind of tool that is used for studying structure of matters, and this is neutron scattering. So I'm going to talk to you about the Institut LAUE-LANGEVIN. Is an international research center based around the nuclear reactor, where we produce high fluxes of neutrons to study the structure and the dynamics of matter. So I've been working there in the last 24 years, and I've been leading the large scale structures group for the last 6 years. And my main scientific interest revolves around the structure of membranes. Now, I said it's an international research center. It is indeed funded by mainly 3 countries, which are France, Germany, and the United Kingdom. And then there is a contribution from a number of other countries, European countries, smaller contribution. And the use of the facility really is proportional, is nearly proportional to the support, to the input of these different countries to the facility. Although there are ways to use the facility, even if one is not partner country. And if you are interested in this, I can tell you more about it later on. Right. So we said the ILL is in France. It's actually in the French Alps, in a town called Grenoble, a town very popular with lovers of skiing, of ski resorts, but also a town which possesses a very high concentration of scientific infrastructure. We have universities, we have public research centers, many companies, and many international research centers, mainly located in the EPN campus, the European Photon Neutron campus, including the European Molecular Biology Laboratory, the European Synchrotron Radiation Facility, the Institute of Structural Biology, and the ILL. And between these institutes, there are a number of partnerships that help users collaborate and using the various tools that we have on campus in a complementary way. And notably, the partnership for structural biology and for soft condensed matter have been rather successful in the last few years. So neutron scattering is, together, we have heard about electron lasers, synchrotron radiation this morning. We have microscopy. It's one of the, belongs to one of these European leading infrastructures for characterizing materials. In Europe, we have about 10 major neutron sources. Then there are about 6 in North America, 5 in Asia, and Oceania. And neutrons, I will show to you how it is really complementary to these other methods and how can be a unique, irreplaceable probe for studying structure and dynamics of materials. The ILL. The reactor of the ILL went critical in 1972. So it has, it's been working for nearly 50 years. Neutrons were discovered by Chadwick back in the 30s, and then over a few decades, more and more sophisticated ways were found to produce fluxes of neutron beams. And since 1972, the ILL remains the highest flux reactor. We have a few more facilities that have come up after that, but we remain as the highest flux reactor in the world. Then in the 70s, also pulsed sources started to develop. We have at the moment the most powerful are based in the UK and United States, and are ISIS and SNS. And we heard this morning that very soon the European spallation source will come online. So it will be a very high brilliance source, much higher brilliance source than the ILL, although the average flux is going to be similar, so the ILL will remain competitive and will remain competitive and complementary with the ESS when this will come online. And indeed, we have strong collaborations with people at ESS to help and to make sure that the facility comes online in the most successful way. Okay, so the ILL reactor, a neutron source that generates about 5 to 10 to the 18 fast neutrons per second, has a maximum power of 58 megawatt. So neutrons are produced by fission, and the material that we use is enriched uranium. So for each neutrons that hit, that starts the fission reaction, 2.5 neutrons are produced, and one of them is used to continue the reaction, and the other one is then collected and used for sending it to instruments for doing the experiments. So neutrons are extracted, are moderated, so their energy, they are slowed down, the energy is reduced, and they are sent to neutron guides, where by reflection, they can be delivered to the instruments. Before arriving to the instruments, they are their energy is selected, their wavelength is selected. They may be polarized. We will see that neutrons have a spin. Their size is defined. They interact with the sample, and then their energy or their direction is varied. And by studying this variation in their energy or in their direction, we can get detailed information on either the structure or the dynamics of the material under study. So here is a top view of the facility. In the reactor dome, we have the reactor core where neutrons are produced. And then we have guide halls where a suite of about 40 instruments are located. So 28 ILL instruments, and then we have a certain number of instruments which are collaborations with partners institutes all over Europe, and that we call CRGs. The instruments, according to the way they work, they are divided in different groups. So we have a diffraction group, a large-scale structure group, nuclear and particle physics group, and the spectroscopy group where dynamics is studied. According to what one wants to see, the instruments will have different optics, different detectors, different collimations. But overall, in all experiments will follow a very simple path of having a flux of neutrons, an energy filter, so something that will select the energy of the wavelength, interaction with a sample, and detection over a detector. So they are basically, the basic components are always the same. And regarding science done at the ILL, is mainly dominated, of course, by physics. There is a lot of work done on magnetism. We will see that the neutron has a spin, so it's very interesting for magnetic studies. There's a nuclear and particle physics. But neutrons have also some very special features that make them extremely interesting for soft matter or biological studies. So we will see that, about 1/3 of the use of the ILL is for soft matter and life science studies. The variety of systems that can be studied is very large. We have more and more work devoted to material science. I will tell you at the end of the talk that we are now finally offering some imaging facilities for material studies. So why are neutrons so interesting, and what makes them different and complementary to other tools, especially X-rays? So neutrons are electrically neutral, so they can penetrate deeply into matter, and they do not damage the studied sample. So they are very sensitive to plastic components because they are very sensitive to hydrogens, and so we can image material in a complementary way with respect to X-rays. The fact that they can penetrate deeply into matter allows the use of very sophisticated sample environments. So we do measurements applying all sorts of external fields. We do measurements, very high temperatures, very low temperatures, high pressures, systems under shear. So we use in situ techniques, and the fact that they do not destroy the sample is obviously very interesting and very precious for biological material or soft matter material. We can do in operando in situ and in operando studies as well. And this is just an image of an engine in action. Then, as I said, the neutrons have a spin, therefore a sensitivity to magnetic properties. We can polarize neutrons and characterize all sorts of exotic materials, materials with complex structures, and materials with complex behavior. Very popular these days is work done on these magnetic structures called skyrmions. The wavelengths of neutrons are comparable to atomic sizes. We have wavelengths that go from the fraction of angstrom for thermal neutrons up to tens of angstroms for cold neutrons and more without neutrons. So we can probe complex structures with sizes of the order of thousands and more of nanometers, as well as we can go down to fractions of the angstroms for looking at interatomic distances. And we do play with the wavelengths of neutrons, so by slowing them down in what we call cold sources or hot sources or moderators. And finally, why they are so popular for soft and biological material. As it has already been said, neutrons interact with nuclei, contrarily to X-rays that interact with the electrons. And if we look at the scattering power of neutrons and X-rays, while in the case of X-rays, it will increase monotonically with the number of electrons in an atom, so will be larger and larger as bigger and bigger is the atom. In the case of neutrons, the scattering power varies randomly in the table of elements, and we have this special feature of having a different scattering from different isotopes of the same element. And this is very much exploited for the case of hydrogen and deuterium, where the scattering is very different. And by isotopic substitution in soft matter or in biological systems, we are capable of highlighting parts of the systems of interest and we can remove completely scattering for other parts of the system. And this is a particularly unique feature. Example, I have a couple of pictures here to give you examples. Here, for example, we can see that we can study low resolution structures of proteins in solutions that are stabilized by lipids nanodiscs. We can make these nanodiscs transparent to neutrons, so we can match them out with the surrounding solution and have signal coming only from the protein inside. Similarly, for the case of polyelectrolyte surfactant complexes, this is some work that came out recently where structure and dynamics was studied. We can get this complex, immerse it in solutions that can match either the surfactant core or the polymer part, the polyelectrolyte part, and then have signal coming only from these parts of the system and study in detail only that part of the system. Or finally, in the case of layered systems, so systems that make layers on a surface, one could study the moving of material from one layer to the other by using this isotopic substitution and changing in this way the composition of the layer as the molecules move from one layer to the other. So the structure of biological soft matter is probed at the ILL by the group to which I belong, which is the large scale structure group that contains small angle scattering machines for studies in solutions, reflectometers for studies on surfaces, small angle diffractometers. Dynamics, on the other hand, is studied by neutron spectroscopy. So with large scale structure instruments, we study structures that go from the angstrom to several hundreds of angstroms. With dynamics, one can study motions from the femtosecond nanoscale time scale to the 100 nanoseconds time scale, using inelastic scattering, backscattering, and spin echo instruments. When we welcome users, we have facilities that can to help them preparing the samples. So in soft matter, for example, we have set up a partnership for soft condensed matter that will offer a number of equipment for sample preparation, delicate sample preparation, as well as complementary characterization during neutron experiments. And for example, within this sort of partnership, there's a development of specific systems. There is a very big program around model membrane studies, and I'm particularly attached to it, where what we offer are ways to properly prepare samples that will have shapes different according to the technique that one wants to use and according to the information one wants to get. So we can provide help to prepare this sample and study them with large-scale structures techniques. And just to give you an example, within this partnership, we've been working in recent weeks on COVID-related science, as has been requested by the management, and there is a big effort in all facilities for getting an understanding on what happens and how to help in fighting COVID-19. So one of the examples we've been working on has been looking at the interaction, as I said, at the angstrom scale, of small peptides, fusion peptides, that are a part of the spike protein, that is this red protein that you see when you have the image of coronavirus, as well as the interaction of the entire protein with membranes that contain a receptor in the membrane capable of attracting the virus and then starting the process of internalization. So we used the surface studies to have a look at that. The analysis is in progress, but already we are capable of having some preliminary results about removal of lipids from the membrane, as well as the structure of the attached membrane to this receptor. Another technique that is going to be used, has been already actually used in the United States for COVID, but it's a technique used for many other things as well, is crystallography from proteins. So what makes this technique interesting and complementary to X-rays is the fact that with neutrons we are sensitive to protons that you cannot see with X-rays. Hydrogen bonding, hydrogens that you don't see very well with X-rays, hydration. So basically what we do when we do our measurements, and the ILL, we do it using a LAUE diffraction instrument. We start from a structure coming from X-rays, and we are capable of putting the hydrogens into the structure and localizing hydrogen bonding or water of hydration. So there's work going on in the case of COVID. We are not doing it this will come next cycle at the ILL, but we have a long history of working on systems involving viruses, in particular in collaboration with our USA colleagues. People here have been working on the inhibition on drugs that inhibit the enzyme protease, that is an essential enzyme in the life cycle of HIV, and is a clinical drug target. So with neutron studies, it has been possible to identify precisely how these different inhibitors link to the protein, and it has been able to suggest different ways to enhance the binding or limit the drug resistance. We are moving more and more towards exploiting fully the complementarity of X-rays and neutrons, and we are acquiring in-house X-ray equipment. So for example, now for a single crystal diffraction, so either from protein or more generally from all crystals, we do have an X-ray diffractometer that allows you to measure exactly the same sample with neutrons and X-rays, and that can be accessed when you have a neutron experiment. Similarly, thanks to the collaboration with the Erlangen University in Germany, and thanks to a BMBF grant, we have acquired a SAX machine that we have installed in perpendicularly to a SANS instrument, allowing us to do simultaneously small angle neutron and X-rays scattering. So here you will see this, I've lost my mouse, the sample position. You will have your sample tilted at 45 degrees, allowing to hit the same spot with X-rays and neutrons that are oriented perpendicularly one to each other. A first paper, so this instrument is, this facility is not yet available to users, but will be very soon in the next year, hoping that we can run properly, but it has been commissioned, and this is already a paper that has come out this year in the Journal of Applied Crystallography, where the growing of gold colloidal nanoparticles stabilized by a surfactant, surfactant myself, has been followed. So these data have been collected simultaneously. With time, we see the increase of the SAX signal due to the growth of the nanoparticle, but a decrease of the SANS signal coming from the surfactant micelle. And this observation helps understanding the polydispersity of the gold nanoparticles, as well as the way they grow, and what's the influence of this stabilizer of this surfactant. And finally, another example where we use simultaneously neutrons and X-rays is imaging. So we have a new instrument called NEXT, an instrument that allows to get to 3 micron resolution, collect 1 millisecond images or 1 second tomography, and that allows to image a number of interesting things. So we have a paper that's come out recently on the localization of water in the roots of plants. A lot of work is done on batteries, and here again we have a paper that has come out this year on simultaneous studies of neutrons and X-rays of real lithium manganese oxidized manganese oxide batteries, and the detailed structure has been possible with X-rays, but the diffusion of lithium is a small element, but is strongly scattered by neutrons, are strongly scattered by lithium, so it has been possible to see the lithium diffusion with neutrons. And there are many more examples, but in 20 minutes we cannot cover much. So I leave you with this summary containing some numbers about the ILL. So 50 years of work, 21,000 publications, about 600 per year. 120,000 visitors, 40,000 experiments. So the countries that contribute are again displayed here. But we have users that come from 45 different countries, and there are different ways to access if one is not a member from a member country of the ILN. And then we have some modalities for applying beam time, but I can tell you more details if you're interested. So thank you very much for your attention.
Thank you very much, Giovanna. And we have a couple of questions, in fact, coming in. And one of the questions is, what is approximate waiting time for from application until delivery of research? Maybe you can speak a bit on timetable.
So when one talks about delivery of research, you mean publication, or you mean when you do the experiments? Anyway, well, I'll give you some ideas. So we have two rounds of proposals submission per year. So every 6 months, one can submit a proposal. From the time the proposal is submitted to the time the beam time is awarded, unless there are special reasons, and one, if you have really very hot science, you can go for some direct or discretionary time, or this sort of, some fast lanes, but normally would be at least 6 months from when you submit a proposal to when you can do an experiment. So starting from those 6 months, in that year you do the experiment, and then depending on the difficulty of the experiment, from there to publication, there is an average of 2 years. Sometimes if you have a neutron diffraction pattern from some powder where you can index very quickly your diffraction peaks, you publish in a much faster way. If you have some complex spin echo experiment, it may take much longer, so depends. But it's very similar to what you would find at synchrotron facilities, actually.
Mm-hmm. Thank you. So similar path in all facilities. The next question is, which are dominant industries that are approaching ILL at a particular moment, or in more human way, the question would be, who are the most interested in neutron scattering?
Okay, that's interesting. There are maybe people in the audience who know better than me the answer. So I am familiar with industries from companies that become interested in for soft matter, so for surfactants, polymers. So you would have companies like Procter & Gamble, Unilever, these sorts of industries interested in polymers or surfactants are very good customers. We have a little bit of pharmaceutical industries, but not so much. And industry of petrol. Yeah, I don't know, and of course engineering. Of course, we do have companies that come here for engineering. I expect that the imaging machine is being just offered for public use. Already tested some industrial users, but I expect that the imaging is going to be more used, so for batteries, materials, cements, and so on.
Okay, thank you. Thank you very much for extremely interesting presentation and answers. Giovanna from France, ILL, and now we are moving forward. Again, changing region a little bit. Our next presenter is NRC Kurchatov Institute, PNP, which is a multidisciplinary research center which conducts fundamental and applied research in a wide range of scientific fields, including theoretical and mathematical physics, physics, interdisciplinary research in nano and biosciences with the use of neutron and synchrotron radiation, molecular biology and biomedicine, research with neutrons, protons and heavy ions, etc., etc. So my pleasure to invite here on our online stage Vladimir Ivanov, Deputy Director of Science from PNP Russia. So the floor is yours. Yes, are we online? There is some kind of sound issue.
Have you seen?
Yeah.
Can you hear me?
Yes, we can hear you. Everything's fine.
Do you see my presentation?
Yes, we see.
It's okay. First of all, I'd like to thank the organizer of this nice meeting to present for the possibility to present the current status and tell a few words about our peak reactor. First of all, I'd like to say a few words why we need neutrons. The neutrons experiment can be split in two large blocks. One of the blocks is where the neutron looks as an instrument which allows us to study the structure and dynamics of the outstanding matter and to see how its matter looks on the atomic level. The second block consists of using neutron as an object of research. Neutrons, as you know, is elementary particle which fill all four known for us fundamental interactions, I mean strong, weak, electromagnetic and gravitational interactions, and therefore to study this interaction we can tell how this interaction works and maybe to use neutron to search the possible new interactions. So we get the property of fundamental interactions, and neutron help us to understand how our world works and how our universe was evolutions of our universe. Okay, if we will tell about neutron as object of research, the study of neutron allows us to get the same information about our world, about our universe, the same as high energy experiment which can be done at the Large Hadron Collider on some another powerful acceleration. Despite the fact that the so large differences in the energy of Large Hadron Colliders about a few tera electron volt, but if you tell about neutrons, we study our universe on the level about 10 to minus 20 electron volts. So despite so large differences in energy, we get the same information, and these two different slides, such difference experiment give us the complementary information about our world, so to get the full information about it. If you compare how it looks with two different experiments, I can present here the demonstration of Richard Feynman, which compares the experiment of colliders. It's shown here. If you take two rather complex devices, for instance watches, and after they collide to each other, we will see the parts which consist inside these watches and try to understand how these watches works. But if you will tell about low energy physics, it's absolutely different study. It's a non-destructive study when we see the macroscopic properties of this these elementary particles. I mean, in my case, neutron. The study is, for instance, beta decay, some magnetic moment, electric dipole moment, and so on. And from this information, we can also get the same information as as we get from collider physics. We will tell about neutron as an instrument to the study of outstanding matter. The neutrons has many advantages to study material because this, first of all, the wavelength of cold or thermal neutron coincide with this distance, value of interatomic distance. Therefore, it is a good measuring device to measure this distance, to measure the position of atoms, and also the energy of cold and thermal neutrons coincide or close to the excitation energy. Therefore, we can use the neutron spectroscopy to study how and what atoms do at their position. Also, the neutron is ideal probe for magnetism because neutron possess the magnetic moment. Therefore, to study how the magnetic moment modify, not magnetic, but orientation of magnetic moment modified in the material, we can get information about the magnetic property of this material. Also, there is some extra neutron advantages. I mean that neutron length wave is not proportional to the, for instance, electric charge of the atom, as it is for the case of X-ray, and therefore neutron can have a higher sensitivity and selectivity to chemical element isotopes. Particular neutron allow us to study the very small light, very light atoms, very light elements, the position of very light atoms, which is not allowed for the case of X-rays. And also, what we need to get the experiment with neutrons. We need first of all the maximum high flux of the neutron, which can be obtained in the high flux reactor, which is, for instance, reactor peak, and the realization of high flux achieved by the very compact active reactor core, about 50 liters only for the reactor peak. Also, we use the heavy water moderator to increase the neutron flux, and therefore the flux of the reactor peak is close to the maximum which is possible for the devices of such types. Also, to get the experiment, we need to prepare neutron with a specified energy which you need for experiment. Therefore, we need some system of neutron thermalization and to obtain neutron with different energies. Also, we need to transport this neutron to the experimental station, so-called neutron gate system, and the neutron experimental scattering station finally will be used to study to make the experiment with neutron. The parameter of the reactor peak, which we have now, is power 100 megawatt. The reactor core volume is about 50 liters. It's so compact reactor core give us possibility to obtain the maximum neutron flux, as I already told. For the reactor of such type, it's reached about 1.3 or 10 to 15 in neutron flux in moderators. And also there is some feature of reactor peak, so-called central trap at the center of active reactor core. There is some central trap with the maximum neutron fluxes about 5 on 10 to 15 neutron per square centimeter per second, which is not allowed in any other experimental reactors. The coolant of the reactor is light water, reflector, as already told, heavy water. Operation cycle, which is expected for when it will be after the commissioning, about 30 days, about 25 days work in the power and 5 days for reloading of the reactor core. There are a lot of different channels, horizontal channels, about 10 horizontal channels to avoid neutrons from the reactor, 6 vertical channels to put samples in the higher flux neutron, thermal neutron. Also, we have some feature of reactor, so-called inclined channel, 6 inclined channel. There are second level under the hole of horizontal channel, so-called hole of inclined channel, and 6 channel provides the neutrons on such hole. And also, as already told, the central trap with the maximum neutron flux about 5 on 10 to 15 Newton per square centimeter. The scheme of experimental channels shown here. We plan to put 2 cold neutron sources as shown here, GEC number 3 and horizontal channel number 2, and also hot neutron source of hot neutrons on the GEC number 8. Therefore, we will get any neutrons which is need for experiment with different neutron spectrum. Hot, cold, and thermal neutrons will be allowed to make experiment with such neutrons. How peak looks at the European neutron landscape, how it will look in compare with another neutron sources which is exploited now or which is planned for construction in the Europe and in the world also. This shows the evolution of neutron fluxes from the discovery of neutron at 32 by Chadwick. One can see that at the beginning there was some saturation now on the fluxes of neutron sources, and the reactor peak is on the maximum on this saturation. So for such devices, which is reactors, high flux reactors, I don't think that it will be possible to exceed this neutron flux in the nearest future. Also, there is a serious progress in the another type of experimental and another type of neutron sources. I mean the pulse neutron sources, based on the evaporation, on the spallation reaction, where the high flux, higher energy protons beams used to get neutron from heavy elements, and you can see that maxima of this cover is more than the continuous sources, which is reactors, but it is fluxes in the pulse. If the average fluxes of these sources in time, the average flux will be even less than for the continuous neutron sources. That is a reactor peak. Therefore, now how will look the neutron sources at the Europe in the nearest future. Now the most powerful neutron source is reactor ILL, but it is expected that during the next 10 years it will be shut down, and therefore all neutron sources which is planned to be at the Europe, it's European spallation source, which give us this pulse neutrons source, and the reactor peak, which has more or less the same, about the same average neutron fluxes. Of course, the ESS has more neutrons at the pulse, but the reactor peak has more neutrons in average and in the mean mean fluxes. So, which is what we expect for the nearest future in about nearest 30 years. Of course, reactor peak should be the international centrum, because to realize all potential of the reactor peak, we need the very large community, because if we will be able to make about 40 experiments at the same time, and therefore about 200 days working per year, therefore we expect about 1,000 experiments which can be done during the year. Therefore, we need a lot of people, a lot of scientists which will be used with reactor as a neutron source, because a lot of experiments. I want to say that already at the first phase reactor peak commissioning, which I show later, which finished this year, already 2 experimental stations in some type of international participation will be commissioning this year. Also, I'd like to say that reactor peak is involved to the Kremlin program, Connection Russian and European Measuring for Large-Scale Research Infrastructure, and the reactor peak is involved to the work page 4 to involve the science cooperation and around peak, the field of neutron sources. The aim of this Kremlin connection with the reactor peak is to propose some neutron experimental station which can be interest for the international community, and to propose neutron gate system for these new stations, and to propose maybe some type of cold neutron source for the channel number 2, which will be also maybe have interest for the international or European community, scientific community. Also, the national instrumentation program, our national instrumentation program, which is under realization now, takes into account the possible international cooperation. And at the neutron gate hall, we have some free area where we can put a few extra neutron beam lines to put here some CRG instruments or something, another variant of cooperation. So we have technical possibility for realization of some cooperation program. Location of the reactor peak is also quite convenient for the international centrum, because it's located about 20 minutes from the airport to Pulkovo near the St. Petersburg, and therefore so the location is near the cultural, industrial, and scientific and educational center of Russia. Therefore, it is also necessary for international community, for international community also. What is our plan and where we are now with the reactor peak commissioning and the instrumentation program? Very briefly. Just now reactor peak is under commissioning. The first step of the commissioning was made at last year. At 19, we reached about 100 kilowatt of the power of the reactor. This year, we plan to reach possibility to get about 10 megawatts of the reactor peak, and in 22-23, we plan to obtain 100 megawatt of the power of the reactor. So during the next 3 years, the reactor peak commissioning should be finished and reach 100 megawatts. It is expected powers. Then, in parallel with construction in parallel of the reactor peak commissioning, the experimental station was constructed. Its diagram for the power is shown here. 100 kilowatt reached at 19. This year we expect 10 megawatts, and around 23 we expect about 100 megawatts power. In parallel, we construct the experimental stations to carry out the experiment. First experiment, very simple and trivial, was made at 100 kilowatt. It's not interesting, but nevertheless. Now the 5 stations of the first phase instrumentation program also will be commissioning at the end of this year. We wanted to construct 2 diffractometers, 1 spectrometer, and 2 reflectometers. Here, about 5 stations. And a main national program for the construction of instruments is started this year, and at the end of 2023, or 2024, 20 new stations should be commissioning at the end of 2024. Therefore, around this time, we expect that the reactor reached where planet powers, and for some serious part of the experimental station will be constructed around 23-24, and the users program can be started around that time. instrumentation program, national instrumentation program, which is realized as the framework of the financially approved national program of the development neutron-synchrotron research, contains all instruments and all sources which is necessary to carry out neutron experiment. 2 neutron cold sources will be constructed at the horizontal channel number 2 and horizontal channel number 3. Also, hot neutron source will be constructed on the horizontal channel number 8, and also some special cold neutron, ultra cold neutron sources, which is necessary for fundamental physics, for the physics of elementary particles, will be constructed on the channel number 4. And also 20 stations, 20 new stations will be made during these nearest 5 years. Experimental station for condensed matter, 13. Sorry. And 7 experimental stations for fundamental physics. The experimental stations for condensed matter consist of all instruments which is necessary to study the outstanding matter using neutron as an instrument. I mean that it consists of diffractometers with different resolution, different energy of neutron, spectrometer of an elastic scattering 5 with different same resolutions and so on, what is necessary for experimental station 3 SANS machines and 2 reflectometers. And also 7 instruments for fundamental physics. I think it's not too so interest for this auditorium, only maybe some I'd like to say, and one I will detail later about this. Okay. 5 stations of the first phase consists of, I already told, two reflectometers. 2 reflectometers, 2 diffractometers and 1 spectrometer. Rather simple experimental station. It will be built at the test model because we not only have to get the power of the reactor, but also we have to demonstrate that we can make some experiment with neutrons on neutron beams. And therefore, these 5 stations will be built at some test, some demonstration model. But nevertheless, if you will get neutron, we will get can make some experiments on this experimental station. And if we will tell about phase 2, which start realization this year, 2 cold neutron sources with horizontal channel number 3 and horizontal channel number 2 will be constructed during this year, this program. They will be constructing different models. This is a vertically loud source and horizontally loud source. Both of them are based on the liquid deuterium, about 20 or 25 liters, with the temperature about 20 kelvins, which will be obtained. Okay, 20 kelvins. That's neutron for cold neutrons, which is interest for the experimental scientists. Okay. Also, we plan to build a hot neutron source at the channel number 8. It will be graphite, about 5 liters of graphite with a temperature about 150, 1,500 or 2,000 kelvins, about 5 liters of graphite. Therefore, we can get temperature neutron with such temperature. And also, we plan to build in beam superfluid helium-4 converter to obtain the ultra-cold neutrons. We plan to obtain the neutron sources, ultra-cold neutron sources, with a density about two orders better than the level. Now it will be the best ultra-cold neutron source in the world for the 100 megawatt neutron power of the reactor. Neutron gate system consists of initially 10 lines, which are split on the many beams position. The length of neutron gate system is about 1 kilometer, and this system allows us generally to obtain about 50 experimental positions with the fluxes around 10 to 10 Newton per square centimeter per second. And one can see that there are many free free beam time, which can be used for some extra experimental station, which is not constructed at the framework of the National Instrumentation Program. Oops. And 2025 experimental station, which will be built during the phase 2 and phase 1 and phase 2 of the National Instrumentation Program, is shown here. Its position on the three different halls for the experimental station. I mean the neutron gate hall, hall of the experimental channels, and the hall of inclined channel. Inclined channel, as already told, is the second floor under the hall of experimental channel, and the neutron beam has directed about 30 degrees to the horizon. Therefore, not neutron scattering experiment can be realized at such geometry, but neutron capture experiments, such as which is shown here as for fundamental physics and for nuclear physics, can be realized in such geometry. For instance, neutron activation analysis and gamma reactions and fission physics. The neutron is captured, and we see the product after what happened after the neutron captured. Therefore, all these experimental should be realized during the next 5 years, and some our roadmap of our instrumentation program is shown here. This year we start. We have to start first 5 experimental stations, 4 stations, and ultra cold neutron source should be started this year. The next year will be started also 6 instruments, and also after next year will be started another instruments. And at the end of 24, all this program should be finished, and we will get all. We have to obtain all system what we need for the neutron time experiment. Therefore, I hope that this ambitious program will be realized, and I expect that at the end of 24 we will get some neutron center, not only reactor, not only neutron source, but also neutron center. They will be able to get and to make any experimental station. So welcome to Gachina, welcome to International Center of Neutron Research. Thank you very much.
Thank you very much to Vladimir Voronin, and for extremely interesting and informative presentation. We have a couple of questions, and one is already the classic from this day, classic question: how to approach reactor pick, or what is the procedure of application for partnership or for the service in particular facility?
Reactor pick, the same as for any neutron source, can be used for any application experiment. I mean, to study any material, to study any neutron, to study any material, and we don't have now some special additional program to use the neutrons in application. We only start with, in our program consists of all instruments which can be used to study the neutron scattering. So it is program is instruments allow us to make any experiments with neutron, with any resolution, with any methodics, and all what we can do with neutron, we will be able to do at the reactor peaks. So at the reactor peak.
Okay, thank you. And the next question also already was asked before, because we are living in COVID-19 era. Are there any limitations at a particular moment for using facility because of COVID-19?
Our facility is not don't have the user program now, so this facility is not be able. Is not user program. We have not a user program now, so this facility is not used by the internal scientists. I hope that at the 23, the COVID will allow us to use to use this facility together with our international scientists. So just now the user program is not used, don't work in our facility. So.
Mm-hmm. Thank you very much, and hopefully really at the year 2023 the COVID-19 will be not on agenda anymore and we will live ordinary lives. Thank you very much to Vladimir Voronin from Russia, and now we continue with a kind of anchor which is moving us toward the next day, which means at this particular moment we will get online with Andris Anspoks, who is Deputy Director for Innovations of University of Latvia, and he's gonna outline the idea of hackathon which starts tomorrow. Andris, do you hear us well, and are you online?
Yes, I'm online. Do you hear me?
Yes, we hear you, and of course the main question is hackathon starts tomorrow. What's the expectations from the hackathon and what's gonna happen?
Yes, that's very great. I welcome you all who have registered for Photon and Neutron Science in the Baltic Sea region online hackathon. Actually, it's a kind of workshop, which is a very friendly event to learn how to form an international team, and the goal is to transform an idea into large facility project proposal. And in this journey, you will be assisted with help of the mentors and organizers of this online event. And also later in this workshop, in this symposium, you will see many examples from biology, medical, material science, chemistry, how to use these applications, these large facilities to real life applications. And in these 3 days, basic outline is rather simple. Please be organized and submit your idea till Tuesday, 3 o'clock Central European Time. Then from 12 o'clock Central European Time, organizers will be ready to interact with you, answer your questions. And at 4 o'clock, we meet all together in a grand opening webinar, and there you'll be explained many things, how to proceed, how to do. And after that, for every team will be assigned a mentor. Mentor will have many teams. And then the biggest working day is usually the second day, which is Wednesday in this case, October 28th. And in the third day, you should submit your proposal. But you will be able to improve your idea, improve your submitted proposal till November 16th. But I really encourage to use these 3 days as a day where you focus on this task, where you get to know each other, discuss the idea, compose really a core team, use most out of the mentors, and also tomorrow in webinar you will be also explained how these proposals are evaluated. Yeah. So this is what will happen next 3 days. As I said, it will not be painful. That's a fun. You should have a fun. And it is a way how to organize an international team remotely working on one idea. And this is how life is. And after lunch, I will tell in my presentation a bit more about how the things happen in real life. What does it mean to use large facilities in real life? Good.
Good, thank you very much. And indeed, the anchor for the next 3 days, it's done, and the teaser was wonderful, in fact. And yes, after the lunch, Mr. Ansvox will speak more on this issue. But until the lunch, we have more presentation to do, and the next presentation will be from Facility Links, which is Links is a valuable and innovative facilitator of collaboration between universities and industry within the area of neutrons and X-ray technology, which is being established in 2016. Links is releasing the great potential of the established industry portal and continue to generate value through many projects, workshops and networks connecting the scientific and commercial world. More in details about Links, I'm happy to give the floor to Jakob Becker Christensen, Chief Executive Officer from Links in Denmark. Jakob, the floor is yours. There is sound.
Yes, I just remembered.
Sound it is. Thank you.
Just remembered now. Thank you very much, Mr. Chairman. I'll just see if I can share my screen here. So thank you, everybody, and thank you for the kind words. I will, over the next 20 minutes, try to talk a little bit about what Links does and how we are structured and how it works and how it can possibly act as a template for what other people might do everywhere, obviously. So I'll just see if I can minimize this bit. Yeah. Can everybody see this screen?
Yes, we can.
You can, good. Mm-hmm. So anyway, as I already partially revealed, I will talk about micro innovation because that's basically what we do in Links, and that is sort of part of the success. Well, it's the key to our success, I would say. I have chosen 2 title screens because why not? The second one is the use of innovation platforms, and that springs from the fact that Links is operating as an innovation platform. Industry portal, yes, but we have actually developed to platform status, and I will talk more about what that means. First, myself, the nice picture. As already mentioned by you, Mr. Chairman, I'm CEO of this industry portal Links. We are a mediator organization between industry and academia. So basically, we try to promote the industrial use and implementation of research tools using X-rays and neutrons. So many of these things are currently sitting at universities, and some politicians in Denmark thought that they might be valuable for job creation and so on if promoted in industry. So that meant that we got a grant, or a grant was released, 6.3 million euro, if my math serves, from this 5-year period. And that is basically the money that we have to have available to disperse in projects. And so far we have 16 companies, mostly Danish, a few in Germany and Sweden, 9 knowledge institutions, 3 technological institutes, and 3 sponsors. So that is basically the club that we have now. And I should mention that club is very literal because Links is actually structured as a non-profit organization to provide a neutral ground for this meeting thing. So our companies are everything from tiny companies, 2 people, to Novo Nordisk, whom have thousands upon thousands and sell internationally. Our factory floor, the driving force behind what we do is that we have 3 Danish universities, Copenhagen, Aarhus University, and the Technical University, connected to us as sort of prime partners among universities. They are there because they have key experience in Denmark. They're sort of the powerhouses of neutron and X-ray knowledge and experience in Denmark. So Copenhagen is very good at small angle scattering and related techniques. Aarhus University is good at crystallography, and DTU at imaging. So that is sort of the triangle that is being pushed to industry by us. We try to help SMEs as much as possible. I will get back to that a little later. And as I mentioned, we operate presently as an innovation platform, also to be defined later. And one final thing, which is not to be underestimated, is that we have a very strong focus on outreach and promotion. And that is necessary because if you think about it, outreach, promotion, storytelling, getting messages out there, universities are poorly suited for that because they do research, they do teaching and so on. There's nowhere usually in that charter that they must do this. Technological institutes, they work closely with industry, so they're not allowed to for IPR reasons and so on and so on. But here we actually have a special organization, us, that are able to tell these stories on neutral grounds, which is necessary, otherwise you don't get people on board. On SMEs in Denmark, just to sort of focus on that for a brief moment, they are usually not motivated to use research expertise, which is sad. They carry less than 10% of all the corporate spending we have in Denmark, and I think this is a picture that is pretty recognizable for most nations. They have poor access to academic expertise, which is of course another thing that links can help them to connecting them to these 3 core universities. And their challenges tend to be simple but crippling. Basically, big companies, they come to us with nice to have challenges. It is something that's somewhere in their project portfolio, but which they want a closer look at to see whether it should gain priority or not. However, SMEs, they come to us with need to have. That is some, challenges that could make or break their company. So that is an interesting distinction. And also for small companies, it's hard to navigate the innovation system, which is why it's good with a mediator, because we can help them doing that. This is just a brief graph just to show that I don't speak out of thin air. This is sort of the research spending in Denmark. And you can see at the bottom of the curve, you have the top 5 companies in Denmark. They carry 30% of all research spending in Denmark. And if you step to the top 500 companies, they carry 98% of all research spending. And the flattening of the curves, of course, shows that there's not really any research spending on the rest, which means that there are zero potential for them to engage in X-rays or neutrons and facilities if they don't get help. Our funding landscape in 30 seconds is that we have one fund which dominates everything. It's called the Innovation Fund Denmark. They also funded us. They have some programs, major, small, some special programs. But if you read down this list, you will see an issue. You will actually see a hole. You see something that is not covered here. And basically, if you see the 2 top lines, you have some huge projects for academia industry, and you have some very small things for research startup. And the bottom line, InnoBooster, that's everything else. So they basically have one program that covers the bulk of all company innovation. So that means that we have a system here which favors major projects and startups, but and the InnoBooster, as was the bottom line, it is there, but they get 300 applications per week, which is not useful or helpful at least. And that means that all the simple small-scale projects which are suitable for InnoBooster, they face very hard odds. They don't get any feedback. They basically just get a stamp that says declined or accepted. And that's a problem, but that leaves also the necessity for something more, something extra. And of course, I'm working myself to the point that links is part of that extra. But if you take all the sum, if you do the integration over all the small scale innovation that's going on beyond the top 200 or top 500 companies, then you actually get quite a width of innovation. The total volume is small, but the width is huge because you have so many companies involved. So that brings me to this point of micro-innovation for my first title slide. It means that we, with LINK, are trying to de-risk simple and practical challenges which are here and now. And obviously here is the subtext which involves X-rays on neutrons. That is because that's our mandate, that's what we're here for. But basically it's about de-risking. It's about people don't want to make that step unless they get some kind of encouragement and unless it is more or less, something they can do without risking their companies, especially for SMEs. So we are part of the counterpart basically to these huge projects, the very ambitious projects that span huge chasms of innovation where we sort of provide a plank just to get across a ditch. that can be equally important. And that means that we only deliberately go for one step up in TRL, so technological readiness level. That's not a lot, but that's enough usually to bring companies to the point where they can actually continue their own development without our assistance. And hopefully having received a good impression of what neutrons and X-rays can do, so it sits in the back of their mind that they might actually use that in the future for different kind of challenges. And it is very easy to get engaged in because you don't have to make, a huge commitment, just getting one step ahead. That's kind of doable. Project examples. The reason why I don't refer you here to a web page is that we are actually changing the web page like this week. So the link is not really existing yet. But if you are interested, you are more than welcome to get back to me, and then I can show you some of the project cases that we are making. But just leafing through projects, a sample of projects very briefly. We're looking at production speed, the packaging machines, that's with Tetra Pak. We are looking at to validate materials for water treatment systems. So basically that's self-cleaning filters for microplasts filtration, mineralization and heat exchangers to provide more efficient heat exchangers ultimately, or better coating to prevent the mineralization. Fiber networks, stone wool, that's Rockwool International. Track and trace and model for water ingression with different kind of plastics, rubbers, and so on and so on. There are many products where people are very uninterested in water getting inside because, it causes all kinds of problems. Barrier protections in semiconductors, antibiotic diffusion in hospital products, and business potential from biochar, from pyrolysis, so that's biogas, thermal biogas production, mechanisms in medical equipment. There's tons of things, and all of these things are basically encompassed with the three techniques of small angle scattering, crystallography, and imaging. Some of these involve one technique, some of these involve several. So that's sort of, and some of them one company and sometimes several companies. So it can be bilateral projects, trilateral, and so on and so on. That depends on what it is. So anyway, I can go into detail with these if you have questions towards the end, but for now, I just want to step on. The whole point of this is that we want people to fail fast and fail cheap if they fail. Small projects, and our projects are only 6 months. That's not very long for an innovation project, but that also means that we need to get started quick and we can finalize it quickly. And that means that they are low budgeted. They are not very expensive, especially compared to these enormous innovation projects that other people run. And it enables the quick decision on what actually works, which means that we, instead of doing one commitment for 3 years in a huge budget, we basically string along larger projects by small ones. So you get 6 months and then you see, okay, what worked, what didn't work. You adjust, you make another project based on that experience, and so on and so on. That means that failure doesn't cost that much. And that means that you can adapt very dynamically, which is very useful for companies. They don't like, the long-term commitments because their budgets, their liquidity, all sorts of things can suffer. Now, innovation platforms, essentially, because that's how we operate. It's a microcosmos, basically, for public-private collaboration. So it's a small sort of a miniature foundation in the foundation, you could say. We are staffed with experts. That's a person such as me. I have a PhD in materials chemistry. Consultants, we are mediators. And we are first and foremost a fast track to co-finance projects. In our case, it is done in the way that we actually have our own money to disperse the project. So we are, in fact, a miniature foundation, essentially, under the Innovation Foundation, our Innovation Fund Denmark. So we can help companies, but there could be other ways to help companies to co-financing. But basically, they need that help. We are not just guides and advisors. Companies, they sometimes choke on the amount of guidance and advising that they get because it actually doesn't lead to the de-risking that is crucial. They don't get, a workable operative plan. They just get a direction. That's not enough. And finally, we and any innovation platform should be a neutral third party, non-profit organization in our case, because otherwise industry can come and claim that we are just doing the university's business and vice versa, because universities and industry traditionally don't always know how to collaborate well, just saying.
Yes, we have some kind of technical issues with Jakob. Most probably the internet has frozen, and we will try to regain connection at this particular moment. Until this, you can easily post your questions in a Q&A session, and hopefully we will get Jakob back in a very short time. Definitely a pretty interesting story considering cooperation, and we would be extremely happy if this connection is coming back to us at this particular moment, because we have also already a couple of questions coming in for Jakob. I will make a contact with the organizers behind the scenes. How are we with Jakob? Okay, we are waiting for signal to coming back, and it will be back in a very short time. So for those who are watching us, we are in the first part of the day. In the first part of the day is infrastructure sessions, when we are speaking on various kind of facilities which are available for scientists and science and experts, and also commercial sector. And after lunch in the afternoon session, we're going to speak already from science and industry perspective, sharing the stories on cooperation and on the way how to build up scientific communities. And at this particular moment, I have a feeling that Jakob is back on track, and we are happy to have you back, Jakob.
Yeah, and my apologies. I don't know what's wrong. I mean, I don't think my network failed actually, but let's just continue. I'm almost done. Just need to leave down through all these things that we already talked about. This is, yeah, I could do this in a more efficient way, but never mind. Good. I don't know where you fell off, but this is the final slide that I showed.
That's the slide. That's the slide, yes.
Good. You saw it, all of it. Okay, good. So stepping on, our advantage is that we have high expertise in the X-rays and neutron business, because otherwise people will not believe us. We do the short projects, we have relatively small budgets, and we have some sensible levels of co-financing, because it's like if you co-finance 10 or 20 or 30%, companies are usually, yeah, okay, but that can still break us if it fails. And that's not helpful for projects they don't want to engage. And again, the TRL, one level, nothing major, nothing massive. And we have very close contact to our funding body, the Innovation Fund Denmark. We have a contact person in the fund, which is basically a very useful partner, because he can tell us whether the projects are good or bad and how to adopt them and adapt them and so on. And these properties are what I would recommend in anybody who wants to, within their country or whatever, wants to define an innovation platform. Look for these things, because that's something where LINX have so far been a living lab showing that this actually can work. So as a prototype, as I said, a living lab for the possible shape of how this can be done. Here's some of the takeaways. As already was mentioned in my introduction, we stimulate some network building, but it's basically and mainly about de-risking. It's about lifting the risk off the shoulders of companies, because then even obscure techniques such as X-rays and neutrons and stuff that to them are obscure, at least to we who are in it on a more regular basis, it's commonplace. But for them, they don't want techniques, they want solutions. So the role that we are playing is that we basically are translators of what the techniques can do into a solution-oriented language that the companies that turn them on. And then you need the de-risking, because they go, yeah, that's fine, you can solve our problem this way, you think, but how do we know? And then we say, okay, fine, we can help you cover some of your expenses, just trust us, we can do this. And then they are actually engaging. So finally, what have we been taught? It's very useful with this consultant mediator role, and a close contact to funding body is very important. They like having a contact person, which is me, and I like having a contact person who sits in the innovation fund. And fund, there must be money somewhere, because otherwise they won't do it. And we, as a mediator, must involve ourselves in every project. They are run directly between companies and universities, but I am there with a guiding hand, and I'm also there as sort of the parent in the room. If something goes completely wrong, then people, you know, sorry, we don't hear from this guy or whatever, you know, people can also involve me. And we have weekly meetings where we update on our projects. And then finally, also the dissemination and outreach. As I mentioned, we need the storytelling. We need all these projects to get out there to share what has been achieved, because that's the way we get to the next companies and see, look what has been done. We can actually help you as well. And then again, what can be done? That's the science of it. You need the scientific skill. You need it to be a persuasive thing. For us, we of course must summarize the impact for the Innovation Fund, and then we have certain goals here, advice on the do's and don'ts for future platforms. That's a big one, and we are asked a lot for now about that. And we want to clarify value propositions to companies, what's actually make them engage, because that's not, in this day and age, this is a fluent thing. It changes over time, but there has not been many good recent experiments on that here in Denmark, at least in this way of doing things. This is my final slide. What is the recipe? You find a funding source. In our case, it's Innovation Fund Denmark. It could be anything, basically, private fund, whatever, but you need money in there. There's no way around the money. You can't just advise yourself way out of this. It is not enough. Then you establish a thematic innovation platform, and thematic, in our case, it's X-rays and neutrons, but it could be anything. It could be robot technology. It could be visualizing product development, or anything. Basically, you could come up with a theme, and that of course needs a base grant, because you need somebody to start engaging with companies who are actually paid a salary even from day one. You need some powerhouses, universities who can actually do that and who have the interface and the connections into the large facilities, and who can also help getting companies in there, not necessarily paying it. And then you need to be careful about who you hire into the platform. You need somebody with high scientific expertise in that theme. In links, that is me. You need some strong outreach and dissemination abilities. We have 2 journalists working part-time. And we also have a scientific writer. We have a layman's writer who deliberately does not have a scientific background. He is scientifically interested, but he does not have a scientific background, which means that he writes our cases that come out of universities naturally in a layman's language, which of course then must be adapted a lot for content, because he doesn't get everything right. But that's extremely useful. So we basically publish 2 parallel lines of cases, one from universities that are rather technical, and one from links directly, which are more layman and solutions oriented. Finally, the next thing and the final thing is, of course, that you must seek out companies. You must present the possibilities. I do that. I sit there with CEOs or managers or whatever. You must identify the advantages of using the techniques, in our case, whatever the theme is demanding of you. And then you need to develop the collaborations and go, yeah, I hear you. You have this and that you want, or you have this and that challenge, or you need something, or blah 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 blah. I think I know a way to at least get you part of that way. So let me talk with people. Let me get back to you. We can set something up like this, and it will not be any trouble to you. Basically, that's what you propose. Of course, it will be a little trouble for the company along the way, and they must do the project. But the whole run up to the project, you need a very solid help and guiding hand, and it basically needs to wash into the front door of the company, because they are too preoccupied with tons of other things if you don't. So that is basically what I have for now. I know that I exceeded my time just a little bit, but since we are slightly ahead of schedule, I believe, then I hope that is acceptable. So I guess this is time for question now, Mr. Chairman.
Yes, it is, and really we have a bit ahead of time, so no problem with the interesting story you are sharing. We have many questions. In fact, I will try to press them in one common question, which is considering the international cooperation, and do you do international cooperations? And as a sub-question to that is, do you help your enterprises with the export strategies and international partners within, if they are interested in and if they need that in the logical development of their companies?
Taking the final project first, we help the companies with whatever we can help them with that has any kind of use or of X-rays and neutrons. And the challenges are really broad, actually. Sometimes it is a product they want to develop on, or they want it faster to market. Sometimes they want some of their processes investigated better so they can assess warranties. Sometimes they want basically just to have better documentation and things so they can make investor proposals. There's really a lot of things. Export, certainly. We have at least two companies that come to my mind who are exclusively selling abroad. They don't have any domestic market in Denmark. JJ X-ray, for instance, some of you will know them. They deliver X-ray equipment for synchrotrons and also for neutron sources. Sole export company. So certainly we do. As for international partners, yes, we do. I mean, we have in Germany we have academic partners, that's DESY, and in Sweden we have Tetra Pak as a company, and we also have RISE, a technological institute, and so on. So some of our international help, you can say, goes via the technological institutes. Directly, yes, too. However, at this point, we are in the final year of links, which means that for now, of course, we need to look towards what is going to happen next. And that next is currently being discussed at different levels. I have no doubt that there will be a sequel, but the exact shape of that is being discussed also among, the officials in the ministry and so on and so on. It is my guess that there will certainly be an international dimension of whatever comes next. But if the funding is Danish, then it is also my prediction that there must be some sort of Danish collaboration, some Danish company involvement. So if bi- or trilateral projects can be done, which involve international partners, certainly. The only thing that's necessary is that you need to be a member of LINKS. We are a club, we are an association, and we're cheap. It's not expensive, let me tell you that. We're not risking people for money, but that's the base requirement, and then you need to assent to the collaboration agreement. Done.
Okay, then we have a question: is there other formations like LINKS, and not only in Denmark, but do you have some kind of organizations abroad which are doing the same as LINKS but in other countries?
The quick question is no, I don't. Not exactly in the same way. There are some big facilities who have nice programs that actually work well with, the industry liaison office, and that is, and of course that lifts some of the stuff off LINKS. The problem is always the funding. That you need the money. So unless the facility X is willing to actually donate money into this instead of making money of it right here and right now, if they want to make that as an investment, then yes. But no, there's nothing that comes to my mind right now anywhere else. And I would like, if any of the participants here know of somebody who are actually doing the same things, there are some things in EU projects, the Carrot projects and so on, but that again, that's mediatorship. That's not sort of the more direct project funding. There's less of that. If any of you out there know anything, then please drop me an email, because I would be interested, also for the sake of the Danish links, to sort of get an overview, get a better overview, because frankly, I'm quite busy with managing the organization right now, so any help is welcome.
Okay, and the final question is, many of the project examples may be very engineering related, and there is need for specific knowledge. Is there understanding enough to cater for those projects? I believe the question is about the expertise. Do you have enough if those are very engineering related projects that are hanged in?
Yes, we have, because the engineering side of it is usually held mostly by the company. It is intrinsic in the projects that they need university expertise. If they just needed a technological service, then there are other people where they can buy that. But with links, it is understood that you need something which has a high scientific level. And the advantage of universities is that they're usually at the forefront. They're developing this knowledge. So they are educating the people who will later on work with it, but that means that they actually have quite a good head start on many things. And they are also quite flexible because they're big. So, I mean, at DTU, our technical university, for instance, it is not only DTU physics, they also involve DTU compute, who funnily enough develop software and computer models. So what we provide companies with basically are research-based tools. Sometimes that can be a software thing. That is quite often the case, actually, a modeling software, which is then sort of handed over to the company afterwards, so they can basically, yeah, okay, here you go. If you do similar measurements, either on in-house instruments or wherever you want to have these measurements done, then you can sort of apply this and you can get the kind of results that you want. A bespoke solution just for you, sir. That's something that we pride ourselves in, but that's of course also a necessary distinction, because in order to legally be able to fund industry or co-fund industry, there must be an academic partner. There must be a public body. And of course, there must be a relevant need and use of the knowledge that public body brings, this university brings. Otherwise, the innovation fund, who funds us, would of course not allow it. So I know that doesn't exactly answer the question, but I think I answered like the 10 sub questions that sort of orbit it. So is there any following up to this, or what do you think? Anything that could be specified more?
I think it's okay at a particular moment, and if there's going to be need for additional answers, then definitely all day long there can be additional questions, and then they will be addressed to you directly. So at this particular moment we are absolutely fine, and thank you very much for your answers. And Jakob Becker Christensen, absolutely wonderful presentation before lunch that we have in a very short time. But before that, before we go to lunch, we have important job to do, which is evaluation of the first part of the day through Mentimeter. So we go to menti.com again, menti.com. You already know the path, the same path, the same way as it was at the morning time. And you can scan the QR code, which is wonderful QR code, beautiful one. You can scan it, and there will be the evaluation survey of the first part of the day, the feedback survey. And we warmly welcome you to fill the feedback survey. We have 2 minutes to do that, so let's be quick. And before we do that, nobody's going to lunch, logically. We know that that's an online conference and everyone is going to lunch in his house, but still, that's the job what we have to do. You can go good old-fashioned way through menti.com and use the code 9670848, or you can scan the QR code and fill the survey. While we are filling the survey, the feedback survey, we definitely can look back on this day, the first part of the day when we were listening for infrastructure session, and research infrastructure session came out with a very basic idea that cooperation matters, definitely matters, the ability to cooperate, industry, academia, and research facilities. And the main thing is that everything is possible, and cooperation is open in all fields despite the COVID-19 challenges. And I believe today, in this first part of the day, we saw a lot of possibilities for building up the common network and building up the common knowledge, even if you are not using the possibilities of particular laboratories or facilities at the particular moment, then still you can build up the contact lists and do this in the future. And one thing we know definitely, that the future will come only through cooperation, and development will come only through cooperation and mutual understanding. Now we are filling up the surveys and the feedback surveys about the first day. There is some kind of chilling music in the background. It means that we are slightly already going to the lunch break, but before that, fill the surveys, fill the feedback, and afterwards we're gonna come back at 1:30 Central European Time, or 13:30 Central European Time, which is in fact in 1 hour and 2 minutes. 1 hour and 2 minutes for the lunch break. That's the momentum. I will make a contact with our green room. Okay, we are still not voting. This is not Eurovision. We are voting in Eurovision. We are still evaluating the first part of the day. So please feel free, do that. It helps us to increase the quality of the conference. We're going to do the next one, the next symposium, definitely. And you can get used to that, because after the second part of the day, after afternoon session, we're gonna do a feedback evaluation again, and after the hackathon, which starts tomorrow, also feedback and evaluation. We are keeping that pretty important, because that helps us to increase quality in the future for the events we are building up in the science network and LaunchPad especially. So if you are just now coming to the screen and thinking what the chairman is speaking there about, then we are doing evaluation feedback, and you can go to the QR code or the menti.com, entering the code in the written way, and do the evaluation and do the feedback. Please do this. We will be extremely thankful for that. Those who are leaving us at this particular moment, please come back in 1 hour, precisely in 1 hour, 1:30 Central European Time, 1:30, we will continue with the session of industry. In the session of industry, we are in this part of the day speaking about the possibilities, the platforms, infrastructures. But in the second part of the day, we're going to speak more on contents, and the contents of science, contents of possibilities which are already used as a good examples for those who are interested in future cooperation, and definitely just building up networks and contacts. That's what we're going to do in afternoon session, which is going to start precisely in 1 hour. And now we are slowly moving to lunch break, but before that, filling up the surveys of feedback about the first part of the day. So the time is ticking. Please do your job. We're going to close the survey in a very short time. So please do your job. We are doing our job, you're doing your jobs, and everyone is happy about that. So definitely in our conference, the first part of the day is over, then lunch break, and then afternoon session. But until this, to get a good lunch, you have to do a great job. Okay, and I have a sign from the green room and backstage that everything is done. You have done your job properly. We have a lot of surveys of evaluation, of feedback. Thank you very much for that. Enjoy your lunch, and we are seeing each other precisely in 1 hour. See you soon. Good afternoon, ladies and gentlemen, dear scientists, community of scientists and experts. We are back on track in our afternoon session. Indeed, it is afternoon. We are back from lunch and we continue in afternoon session with an industry experience, industry stories, which are we sharing within the conference Photon and Neutron Science in the Baltic Sea region. My name is Martin Daugulis and I'm absolutely happy to serve as a moderator in this intense day when we are sharing very informative and very rich information considering abilities to cooperate and build common developments in the field of photons and neutrons and science in the Baltic Sea region. Before we continue with the content, because this afternoon will be really content driven afternoon. The first part of the day was more about the possibilities of infrastructure. This part of the day will be what we can do with this infrastructure. But before that, some technical matters. The first is we kindly ask you to post your questions in a Q&A sessions for each speaker. You can post your questions through menti.com. Those who are with us from the beginning of the first part of the day, you know already what to do, but those who are joining us from anew, then you can post your questions using menti.com. Just scan the QR code, which is in the right side of me, and you will see wonderfully the possibility to post your questions. More than this, even if we do not answer all the questions, because questions are coming a lot, if we are not answering all of them, then they will be answered after the conference. So each question will, which is addressed, will get the answer. So that's the good news. That's the good thing. More than this, the record of the conference also will be available for all participants shortly after the conference. So if there is some details or nuances, you will be able to re-watch them like in the Netflix, but just this kind of conference binge watching doing. And of course, we are speaking on network building and the contact making. All the speakers will be in a one pager. Their contacts will be available for participants of this particular symposium. So also in your emails after the conference. So contacts, information, everything on answers on the questions, everything of that will be available to you. So we are in the afternoon session dedicated to the content. This is the first day of symposium. Tomorrow starts also the hackathon, which will gonna go for 3 days, and it means that we are ready to start. And I am absolutely happy to give the floor to Mr. Andris Ansvoks, Deputy Director for Innovation of University of Latvia, as the first speaker in the afternoon session. Andris, the floor is yours.
Thank you very much for kind introduction. Let's start the journey. So before you have listened about scientific and technical capabilities of the research infrastructures, and after my presentation you will hear a lot of interesting scenarios how these large facilities can be applied to real-life situations. At the same time, you saw and you will see many methods like Fourier transform, infrared spectroscopy, UV to soft X-ray spectroscopy, X-ray photoelectron spectroscopy, XRD, wax, SAX, bio-SAX, macromolecular crystallography, X-ray absorption spectroscopy, XMCD, tomographies, coherence, bioimaging and different nanoimaging, nanospectroscopy, microscopy tools. It's a really big thing, and sometimes it's a question. Oh, that's okay. That's okay. Fine. Is this really for me? Is this why really to bother? Many of these things I can do in my lab, or in a neighbor's lab, or in neighboring institute. And this presentation is a bit about that yes, it is for you. And the most important thing, of course, always is the goal. What kind of goal? Are you developing a new kind of battery? You are researching a greatest medicine for a cancer, and you know you need to understand the exact structure of some proteins or what's happening in particular materials like steels or whatever under different conditions. Many things you want to monitor, not like in time of operation, you know, like cycling battery or pushing some mechanical stress on the steels. So at the end, you are measuring something which is physics and chemistry. And you know, these large facilities give you the right size, the biggest guns available in our research to do the job. And believe me, it is really, really worth to do it. So when you come to experiment, it's a bit like sit in the jet plane. This is, by the way, the Air Baltic's plane. When it was not a COVID times, I was sometimes traveling, you know, and I have a friend of mine was a pilot. And I once had the privilege to be there. And I said, oh, how you can do this? This is so complicated. And the same is like when you come to the large facilities, sometimes you feel this is really complicated job to do. And the main objective of this event is to help you. And we all will help you and use all these contacts you will have for the speakers, participants, really network. It's not easy, I know. It's an online event and where we are all on site. We can have a common lunch, coffee breaks, and we can discuss. But still, I think there are possibilities to do the job, you know. And there is always a question, so, okay, what can I do? How? When? What? What to do to use these things? And as I said again, it's the question is, what is your goal? And after that, you can understand what you really are interested in. And usually these are some physical properties you are measuring, structural or chemical, like valence states or neighbor, what are the neighboring atoms, things like that. And then you must select the best combination of the methods to reach your goal. Yeah? And you know, when you come to this big tool, surprisingly, you must, in many cases, specifically design your sample. Yeah, the sample must be designed for this particular measurement in these large facilities to reach your goals. And the sample should be selected in a right procedure, tested before, not just come and see, because I will comment again and again. This is, when you come to large facility, this is a single shot thing usually. Unless you are paying for it. You can pay once, you can pay twice, you can pay third time, no problem. But when you apply with a project, you will give a unique opportunity, and during this time, you said you must use it. So this is why these most important things include not only the selection of the methods, but also design of the sample, the setup, equipment you will use on site, and also to do a feasibility study before you go. Sometimes even before you consider to write a proposal and to have a set of references, because you must be sure on site that you are measuring what you want, and you are measuring some known references where you know what you expect, what should be the outcome. You know that this is what the first step. Yes, I sense it. Next step, I go to the frontier and challenge the equipment itself. So why it looks so complicated? Because if we look on the life cycle, which is, by the way, rather realistic also in your case, you prepare a proposal. Of course, you have an idea, you think about the methods, but you submit it usually somewhere January, February, depends on the facility itself. It's, let's say, average February. Then you wait till May or June till you receive answer, you are granted or rejected. And then you discuss with the beamline scientists where put in the calendar your experiment. And the experiment happens for the proposal which you submit in February, let's say somewhere in September, December. So it's 9 to 12 months after the submission, you go to experiment. So, which means that you should really be careful about the planning, because this usually is not a solution where you go to answer the very fast and urgent questions. Some facilities offer quick access. Some offer quick access for money, some for some competitive project applications as well. Things happen, but normal procedure, it's 9 to 12 months before you get to the beam time. If you are accepted, and afterwards you do data analysis, do reporting, you must report, but also to the beam time, to the synchrotron or neutron source. And then you do publication of the results or other next steps, which are usually for innovation projects, where you don't publish sometimes too much. So why it is? So this is why the feasibility studies, which are very often omitted, are very important in this case, because you have a huge time frame. And it's very important before you even submit your proposal, before you even apply for a beam time, is you should understand, looking from the perspective of your goal, what you are going to measure and how, and is it really measurable? Is this effect, property, whatever you want, can it be measured? And if can, how it can be measured? And then looking on a particular method, you must understand what will be the composition or design of the sample. Because if whether you need a very smooth and clean surface, or you need the substrate, there is a film on a substrate, and this substrate should be transparent to certain, let's say, X-ray range or UV range or infrareds, yeah. So, and what special equipment you need, power supplies, cryostats, cryostat, if you want to apply a voltage, that all should be planned in before and assessed whether it's viable or not. So what I usually recommend is do modeling. Modeling today is a rather cheap exercise, so the software and hardware becomes so powerful, you can model things theoretically, so it gives you estimate of the size of the effect you are looking on, which is very important. Also, you will narrow up the range where you should measure, what to measure, where to measure, and then you also understand how to analyze the data. Yeah? This modeling can be quantum computing, can be some thermal analysis on finite elements, whatever. It depends what you are really looking for. But this improves your quality of everything. And even I would say more, if you are for a research, for example, you can even prepare a publication before based on your predictions. Sometimes it's even good to do so. And it's an important point, because it's a point where you think go or not to go for an experiment. And if you go for experiment, what setup you need? Because sometimes you see that maybe the effect is so tiny that most probably maybe it's too tiny to be measured. Yeah, but sometimes you find that despite it is tiny, if you apply a particular setup or preparation, you will get the result. So as I said, this experiment is a one-shot show, so it's good to be prepared. This is why you need the feasibilities. in these feasibilities, also it's you, if you can, you test everything in lab. That's also very important. Also, the references, which are the compounds with known effect, state, composition, balance, whatever is required. If you go for chemical reactions, it's good to have all the states or the chemicals you have during these reactions to have as a pure substances as a references. This will be used to calibrate equipment, and this will be used also as a baseline to understand where we are in our system, in our battery or fuel cell or a steel object, whatever you go for. So the actual lifetime is a bit more complicated. It's when you start with idea, you already start with feasibility tests, modeling, initial design, initial team setup. Then you find out, yes, we will go for it. Then you start, write your proposal. Then you do your samples, test, design, do some laboratory work. You receive, yes, you have a beam time. Then you update plan. Now you start a real sample fabrication. You have 3 to 4 months to do it. You prepare and set up and test your special equipment, references, and then you know where is your experiment. You assign the beam time. You finalize your team who will really go. You finalize the plan for the time you received. You do the tests, and you select, based on these tests, you select the right samples, equipment, and references, because it's good to be there with all the confidence. You know what you do, your plan, you measure reference, other reference, then your sample. And during experiment, which is very important, you should have a team able to do on-site analysis. So you compare your results with references and be prepared for unexpected. Because sometimes people get the data, come back and say, oh, we missed some point which is point of interest. It's good to know on site so you can make a small corrections in your measurement plan and voltage or temperature or pressure scale. And then you got the right results, not missing some things you think are interested. Sometimes the unexpected is no effect. Things happen. Afterwards, you do data analysis and reporting, and you continue analyzation and characterization of samples, including what I call post-mortem, which is look on the samples which you measured in synchrotron or neutron beam again. What are they the same? Are they changed? Is this what you expect? And then you go further. So, okay, but if you look carefully on the name of my presentation, you might ask a question. Where is the story about Latvia? Yes, it's coming. So in Latvia, we have no large research facilities. We had once a neutron reactor, but it was shut down in the previous century. But at the same time, there is a steadily growing number of publications, mostly related with synchrotron light sources. How it can happen? This is because of passion and long cooperation history. You know, the passion is one thing which drives the progress and the research. You know, and there are guys like Juris Purāns and Alexei Kuzmin who started in 1980s. And they started to use a new method called X-ray absorption spectroscopy. And they started in Soviet times in the Russian synchrotrons. Then the borders opened when we gained independence. They moved to Italy, Italian synchrotrons, French, Lood near the Paris one. And during these things, passionate people at that time also write their own software code to analyze the data, to understand how to do the experiments, exchange their experiences with Italian and French teams. And this passionate and talented people led to an international cooperation, led us like one of the leaders in X-ray absorption spectroscopy methodology, despite we have no synchrotron here. In 1994, we set our first software package. Then in 2009, we start to combine molecular dynamics and X-ray absorption spectroscopy. And in 2012, we made a reverse Monte Carlo analysis tool. And today, I would say we reached this. And as I said, we also are experts in our institute in optical spectroscopy. And once we had also a neutron reactor, as I said, and we have a good legacy in radiation defects. To understand what's happening there, we must have a theoretical calculations and by optical spectroscopy analyze it. Anatoly Popov, Vladimir Pankrotov use these same skills also in synchrotrons, where you also can use UV, soft X-ray, or infrared spectroscopies. Yes, you can. If we did, you can do it as well. You can become experts, you can team with experts. And many experts, including us, are very open for cooperation because, you know, it's if you look on the next steps, what you can do, apply with your idea and combine a team. Yeah. You can contact experts, as moderator said, there's a list of people who presented in this synchrotron, list of participants participating here, great international team. And believe me, it's not a problem to contact high experts because everybody wants to be a part of a team with a great idea. If you have a great idea, I think there is no problem for you. Thank you for attention. Any questions are welcome.
Thank you. Thank you very much for such a very, like a map, in fact. You can take this presentation and take it as a Waze or Google Maps or something like that and go forward. We have questions, and the question is, what are the biggest mistakes people do in proposal writing, feasibility, and the time planning? Or is there some kind of usual mistakes people could do within this process?
I think about the proposals, it's you must have really a good idea. The good idea rules everything. That's the most thing. Otherwise, it can be very practical idea. That's also is okay because we need to develop things. But most common come with untested samples. And they haven't thought about how the samples will be used in particular setup, because this requires interaction between you as a team, not a single person, which is on the beam line. And you both should communicate. And this is important thing. And second thing is you should do this feasibility because you must test before you come. Yeah, and maybe the sample should be really good. One thing. Second thing, the feasibility, as I said, apply modeling. So you know where to look for the effect. You know, sometimes this change in very small peak in a spectrum is the big effect you are looking for. Okay, thank you. I hope I answered, but that's another presentation.
That's another presentation, exactly. Anyway, if there is some questions which are left unanswered, then afterwards organizers will address them directly after the conference either. We have another question, how to boost cooperation from state perspective, from the state level perspective. Some extra things you can do to boost the cooperation.
From state, that's, yeah. The public administration has a couple of tools, and I think the biggest tool is money, you know. And if they pay, let's say, a part in some large facility using all these that's I think is the best thing you can search for, because then you have a kind of quota for your country. So you have a lower competition, you have national competition, that's okay. But this allows you to bring in users. You can use small fraction of this quota for the training, for the PhD students, let's say, to have them a feeling. If you don't want to do it, you can fund your students to attend a good young students or young researcher or summer schools. Let's say there are summer schools for most of the large facilities. Some of them are really famous, having also hands-on things. And if you pay, it's easier. Then you compete for free. And the third thing is it should be kind of part of education system. So if it is part of education system, then you can do it. For example, if you want to create a users for European spallation source, then you must teach the next PhD students, which will be ready after 2 or 3 years when the things will come in operation, to be ready to understand these methods and buy some neutron time in existing neutron sources to do the training, let's say. That's tough job. It's money, you know, and otherwise it's events like this. That's the softest way how to do it.
Okay, thank you.
But then it's based on enthusiasm.
as it always.
And other funds.
Funds and enthusiasm. That's it. We have also one of the questions about advantages of small states without facilities. What could be those advantages of the countries which has no facilities, and where's there's a pluses and wins?
I think there is not a big advantage, because the best is you invest as a small country in a beam line. Estonia do so. They invest in UV or hard UV spectroscopy beam lines in DESY, now I think in MAX 4. And they do it together with Finland, so they have their own dedicated equipment there, which is open to general public, but they have their quota and access. And that's the best thing any country can do, big or small. But as I said, Finland, Estonia, that's an example how small countries can do it. The other countries is they can support the teams who have passion and experience in this. Creating from a blues, creating from nothing, it needs an investment in, as I said, in education, and then you must somehow make people used to use these things, and that's not so easy, you know. And it's better to support those who already do it. Yeah, that's the second way. Then, of course, you can do nothing. Free market of European projects, national projects. Some of them maybe will be targeted, but that's a Brownian motion.
Okay, thank you. Thank you very much. Mr. Andris Anspoks, Deputy Director for Innovation of University of Latvia, and wishing well also for the hackathon that starts tomorrow. Now we are moving forward and remaining again. This was a very good Q&A session. Questions were coming in also for the next speaker. Please post your questions through Mentimeter or menti.com and post your questions there. It will be highly appreciated, and then we have very interesting discussions. And now we are switching over to a professor from Norway, Inari Kursula, Professor, University of Bergen, which is going to speak on using photons and electrons to understand malaria parasite motility. So very real story behind photons and electrons. So Inari, the floor is yours. We are absolutely happy to have you here.
Thank you very much. I hope you can hear me.
Yes, we can.
And I hope you can see my presentation.
Mm-hmm.
Yes, I have labs in Norway and Finland, so also two smallish countries who don't have any large facilities for photon or neutron science, but yet we are quite big users of European facilities. So today I'm going to tell about how my lab is using photon science and also not neutrons but electrons to understand the malaria parasite motility. Motility, so the ability to be able to move from one place to another, is very important for all of us, from us humans to other living creatures, all the way to small single-celled organisms. And we humans use muscles for this, but of course things like malaria parasites, which are actually just composed of one single cell, they don't have muscles, but they use other kinds of mechanisms for this, and yet these mechanisms are based on very similar biochemical functions as our muscle contraction. And a major protein important for all kinds of motility is actin, which is depicted here in cyan color. And my research is focused around actin-based motility, and this is what I'm going to talk about today. Here you see actin in its monomeric form, so a single molecule of actin, but actually this is not the functional form of the protein. Its functionality is based on the fact that it can form these beautiful long filamentous structures which are very regular. And here you can see an electron micrograph depicting these filaments, which in our muscles can be tens of micrometers long. Excuse me. But in the malaria parasites, they are very, very short. I'm sorry for the dog, we just have to ignore him. Actin and its ability to produce force for motility has been studied extensively in many organisms, and typical model organisms come from a very narrow branch in the evolutionary tree, and that includes animal actins and yeast actins and some other organisms. But very little actually is known about the function of actin in other more simple organisms. So that's why when I started my own research a bit more than a decade ago, I decided to start working on something which is very different and which maybe not so many people are working. And I decided to choose the malaria parasites as my model organism. The malaria parasites, as I said, they are just a single cell, but they have a very complicated life cycle. They need two very different hosts to complete their life cycle. They need a human or another vertebrate, and they need a mosquito. Of course, because the life cycle is a cycle, you can start it from anywhere, but I tend to start explaining the life cycle from here when the infected mosquito takes a blood meal from a host. That's how it delivers the parasites into the body of the host, in this case a human. And the form that the parasite delivers the mosquito delivers to the human is called a sporozoite. And these sporozoites require a certain form of motility, enabled to first get from the skin of the host into the blood circulation, from the blood circulation eventually into the liver, where they go through their first so-called exoerythrocytic cycle of reproduction, and then again to the blood circulation and start invading red blood cells. And this is already a different form of the parasite. During the blood cycle, the erythrocytic cycle, the parasites form gametocytes, which then are taken up by a new mosquito. And in the mosquito, then the parasites complete their reproduction with a fusion of the gametes, of the zygotes, and formation of first these things called oocymetes, which again have to move to get out of the gut into the salivary glands of the mosquito. And then they can start a new cycle infecting a new human host. And during this life cycle, as you can see, the parasite looks very different at different stages, and it requires to move in very different environments between two very different hosts. So my research is aimed at understanding how this really works, how the parasite reaches the goal of moving inside the host organisms and invading their host cells. Here you can see sporozoites. So this is the first form of the parasite that the human host encounters. And here they are gliding on a glass slide. And their motility is indeed called gliding motility, because as you see, they glide very, very smoothly and very rapidly without any visible protrusions from the cell, without any kind of muscle force. It's very hard intuitively to understand how the force for this kind of motility is produced. These are also among the fastest moving eukaryotic cells. They move from 1 to 3 micrometers per second. So how is force for gliding produced? Actin is known to be involved, but it's very different from other types of cell motility. Here you see another type of single cell moving. And in this case, actin is producing the force for motility. And it's somehow intuitively fairly easy to understand that the ability of actin to form these long filamentous structures enables it to grow into these filaments at the edges of the cell and push the cell forward. But this is completely different in the parasite. You see that there is nothing like that happening here. There is no cell edge which is protruding from the parasite. So how does this work? For about 15 or close to 20 years, there has been a kind of a working model of how parasite motility could work. And this involves actin filaments, which you can see here as yellow, acting as kind of tracks for a motor protein called myosin, which moves along actin and can produce pushing forces. Also, the whole motor involves many other proteins. It's linked to 2 biological membranes, the plasma membrane, so the outer membrane of the parasite, and something called the inner membrane complex of the parasite via many different proteins. And via the plasma membrane, it is in contact with host cell surface receptors of, for example, the human host cell. And the hypothesis that we have had for a bit more than a decade is that myosin, indeed, it performs this so-called power stroke. It steps along the actin filament, pushes the actin filament backwards towards the rear end of the parasite, and that results in a net forward movement of the parasite. Of course, this mechanism is in reality much more complicated. For example, the parasite also needs to release, so there have to be proteases in the membrane which cleave the entire machinery off from the membrane. But this is the basic hypothesis which we have. Actin filaments serve as tracks for myosin, which uses its power stroke stepping movement to produce the force for this gliding motility. It has to do this in a very fast and efficient way to reach this, what you see here, the circling of the sporozoites. So the aims of our work in my lab are to understand the mechanism of actin polymerization, how actin forms these filaments, the tracks, and how actin and its regulatory components have evolved in the malaria parasite and also in eukaryotes in general, because they are so far apart from us, for example, in the evolutionary tree, like I showed. We also want to draw a complete molecular picture of the entire glidiosome, so the whole protein complex which is responsible for this movement, and to understand how force is generated by the myosin and the whole machinery and transmitted into the smooth gliding that you saw in the previous slide. And of course, because we're dealing with something like the malaria parasites, which are such deadly parasites affecting large parts of the globe, we want to also evaluate whether the glidiosome, motor, and the actin and its regulatory components could serve as candidates for drug and vaccine development against malaria. So what is so special about Plasmodium actins? Why to choose this system? Actins are in general very conserved proteins, so they are nearly identical between all eukaryotic cells. But the Plasmodium actins have a rather low sequence identity to us, humans, our actins, and also between the 2 actin isoforms which are present in the malaria parasite. And when I say low, this is low in the actin field, so it still is close to 80% identity. But for example, yeast and human actins are way more than 90% identical with each other. A very peculiar feature of the parasite actins is that they form very short filaments, which are in the range of about 100 nanometers, whereas the filaments that I showed in the beginning of this presentation, they can be, as I said, tens of micrometers long. We also found out already a couple of years ago that ATP hydrolysis and phosphate release pathway seem to be different in the parasite, and I'll go more in detail into this in a bit. Also, we have shown that polymerization is not governed by ionic strength in the same way as in canonical actins, and that stable dimers are a significant species in addition to these filaments, which has not been seen for any other actin. But today I'll mostly concentrate on the question, why are the filaments so short, and how does ATP hydrolysis and phosphate release work in these parasite actins? Before I go into the parasite actins, I have to explain something very fundamental about actin polymerization in general, because not all of you might be familiar with it. So here you can see a very schematic view of a canonical actin molecule. You can maybe recognize it from the picture I showed before, and a molecule called ATP is very important for the function of actin. And in this film, ATP-loaded actin is colored in yellow. Actin is actually an enzyme, and it catalyzes the cleavage of the bond between the two terminal phosphate groups, so the catalysis of ATP hydrolysis into ADP. But as a monomer, it's a very poor catalyst, so it needs to go to the filamentous form to perform this catalytic function. And when actin concentration gets high enough, there's a spontaneous formation of a nucleus, which initiates polymerization. And when actin polymerizes, it goes through a conformational change, which activates the hydrolysis of ATP to ADP. And ADP actin here is depicted in blue. And when ATP is hydrolyzed, then that induces another conformational change, and actin filaments are destabilized and depolymerize. So this is how it functions in canonical actins, and that's the basis for this directional growth of actin filaments and how the filaments can, for example, push cell edges forward. But this seems to, as I said, work a bit differently in parasite actins. We discovered already quite a few years ago that in Plasmodium actin, they actually form these short oligomers in addition to the filaments, and they form them very, very quickly, and that this is actually linked to the hydrolysis of ATP. And we also found out that ATP hydrolysis does not require the filamentous form to happen. So it happens also maybe already in monomeric form, but definitely then in the short oligomeric forms. And this is really interesting because that would kind of be against the dogma of how this directional growth of filaments can work. We then solved some crystal structures using synchrotron radiation of Plasmodium actin, both with ATP and with ADP, and we found out that there are some differences in the active site. For example, there is this asparagine residue, which is unique to the parasite actins. It's hydrophobic, so a very different residue in, for example, human actins and basically all other actins. And this asparagine residue actually moves when you go from the green ATP form to the yellow ADP form in this case. There are also many other things that move in the active site, and this we can see in the next slide. Let's see here. Here's an overall view of movements that happen when hydrolysis from ATP to ADP happens. And we paid attention mainly to this loop, which you can see on the foreground here in yellow, because this loop makes a large movement upon hydrolysis from ATP to ADP. And in the lower film, you can see some of the more detailed movements of side chain. For example, here, the movement of this asparagine residue that I showed in the previous slide. We figured out that if we block this movement of the loop, maybe then we can affect ATP hydrolysis. And we thought that if we can actually block the movement, maybe we can stop ATP hydrolysis or at least slow it down. So we made a mutation introducing a large residue instead of a small residue close to this loop. And that would be an alanine to tryptophan mutation, which we thought that would block the movement of this loop. We also mutated another residue, namely this histidine on the other side of the loop, thinking that might also affect the movement of the loop on the other side. So we measured phosphate release rates from these mutants, and actually it worked completely opposite to our hypothesis. So this mutant, which we thought would slow down or maybe even block phosphate release, this was actually so-called hyperactive mutant. And the other mutant, which we thought might actually work faster, that actually was a completely or nearly completely dead mutant. So we had to look into this a bit more in detail. And we called this loop A loop, the one that is moving a lot, because it has this aspartate and arginine residue, and there was no loop called the A loop yet in actin. There are many loops named with different letters. And here you can see the residues that we mutated. There's this small alanine here, which we mutated to a tryptophan, a large residue, and there's this histidine over here, which we mutated into a glutamine. In our original crystal structure, which was in complex with calcium, which is a non-physiological state of actin but helps keep it monomeric, this was the position of the A loop. So the A loop is interacting with this histidine residue. But we decided to determine more physiological crystal structures, meaning we determined structures in the presence of magnesium instead of calcium, because in the cell actin is in complex with magnesium, and this would be the active state of the protein. And in complex with magnesium, we first of all, we got a mixture of ATP and ADP because the hydrolysis starts to happen in the presence of magnesium. And there we actually see 3 different conformations of this loop. And we call these conformations 1A and 1B, which are closer to this histidine, and 2A, which is this loop interacting with this lysine residue over here on the other side. We also eventually got a pure ADP structure, and here we see that the loop is even more interacting with this lysine over here, and the interactions with this histidine are even weaker, and the conformation 1A is missing completely. What about the mutants? How do they then look like? We saw that on the structural level, our tryptophan mutant, it worked exactly like we presumed it to work. So it locked this loop into this position. So we only see the conformation 1B. And the other mutant, this glutamine mutant, that is kind of interacting with both, but it still is only one single conformation. So you remember that this conformation is hyperactive and this conformation is almost completely dead. If you look at actually what happens in filament when we have afterwards also determined high resolution cryo-EM structures of the filament, you actually see that this loop is closer to this lysine over here, but there is another residue that comes into play in the filament conformation as well. We also looked into what the A-loop mutants do for the filament length. And whereas the wild type actin, the parasite actin, mainly forms these very, very short filaments and only a couple of very long filaments, we saw that, like we would have expected, this mutant, which is hyperactive, it forms long filaments, they are more stable, and this mutant, which is catalytically almost dead, that doesn't form filaments at all, or some very short filaments. So we can actually say that the movement of this A-loop is linked to phosphate release and filament stability in the parasite actin. This movement of the A-loop, it has not been seen in any of the canonical actins, but it may still happen, but it's probably not as favorable due to two small amino acid differences. This lysine 270, which is the other interaction partner of the A-loop in the parasite actin, is a methionine in canonical actins, which would reduce the favorability of the loop interacting with this residue. And on the other side, the histidine residue is methylated in muscle actins, which has a large impact on the properties of this histidine residue. So we can conclude that it's these small differences that increase the mobility of the A-loop, and the mobility increases the phosphate release and decreases filament stability. So that part of my talk dealt with how we used photons, photon science to learn about actin. But what can we use electrons for? We cannot crystallize the real filamentous form of actin because they form these long filaments which are not regular in length and they cannot be crystallized. They are way too flexible for that. So we need to use a technique called cryo-electron microscopy for this. And we have very recently determined a cryo-EM structure to a very, very high resolution of the parasite actin filaments. As you can see from this map here, regions of the actin are close to 2 angstrom resolution, and even the lowest resolution regions are about 2.5 angstrom resolution. So we're getting close to, very close to atomic resolution already with this technique. So what can we learn from this? How far can we push the resolution? We can see water molecules in the core of the actin, and this is a very interesting string of water molecules because we actually think that this could be an alternative path for the leaving phosphate group, because the path leads from the phosphate, which is supposed to be hydrolyzed, towards the solvent, as you can see here, and this is the cavity shown in red. When the actin is in its monomeric state, you can see that this cavity is short. It does not extend all the way to solvent. So it actually needs the filamentous form for the cavity to open all the way to the solvent. And I see that I'm running out of time almost, so I'll start with my summary now. So Plasmodium actin, it follows the classical nucleation elongation pathway for its polymerization, for its ability to form these long filaments, but it has this mechanism by this A loop, which leads into destabilization of the filaments and a very high fragmentation rate, which leads to the short filament length. There are the subtle amino acid changes, which I said, the lack of methylation of this histidine, and the methionine residue replaced by a lysine in the parasite, which enable the fast switch between the A loop, between stable and unstable filament conditions. And a similar mechanism is possible in canonical actins, but probably this movement happens at a lower frequency. And we also discovered by cryo-EM that there is a channel in Plasmodium actin, which is gated by 2 residues, which could be the path for the leaving phosphate. So what are our future perspectives? So next, I mentioned already briefly in the beginning, there is a second isoform of actin in the parasite as well. So we want to study that in more detail as well. And we already have high resolution cryo-EM structures of actin-2 as well, which we are currently analyzing. We also want to perform mutagenesis studies, both in the active site and along this possible leaving route for the phosphate. We want to determine structures with different nucleotide states, and this is what we are already doing, and hopefully also trap the leaving phosphate, which is probably very challenging because once it is hydrolyzed, it probably leaves very quickly. We want to achieve even higher resolution, both using crystallography and cryo-EM, and we also want to look in more detail into the catalytic mechanism. So all this work would not have been possible without my research group, and I want to thank every member of my research group. A lot of the work that I presented here was performed by Esa-Pekka and Juha, who have already left my group, and the actin project is now actually mainly continued by Eze here, who is a new postdoc in my group. And because this meeting is dealing with these large infrastructures, I of course have to once again underline that none of this work would have been possible without synchrotrons, without access to these infrastructures. And we are mainly using DESY and the EMBL beamlines over there, diamond light source, and we have also access to cryo-EM via INSTRUCT program. And in the end, I'd like to thank you and take any questions that you might have.
Thank you. Thank you very much, Inari. We have many thanks for interesting story, interesting research, and a couple of questions either. One of them is, what would be your advice to new scientists that only start using photons and electrons for research from administrative and organizational perspective? That would be the question.
Yeah, I think it's actually fairly easy to get access to infrastructures. The synchrotrons have open calls. Instruct has open calls for cryo-EM research. So I would recommend you just to look at the websites, look at the calls for proposals, and if there are things which are unclear, it's always good to contact the beamline scientists and ask them to maybe give you tips for preparing your call. But I think you should just take the initiative and apply for beam time or apply for microscopy time.
Mm-hmm. Thank you. The other question is maybe the same, but a bit more negatively formed. What was the most difficult at the beginning of the research, where the most of your own energy was going to? Like, what was the burning energy going where at the beginnings of research?
In the beginning, in the kind of research that we do, biological research, typically the big threshold in the beginning is to get the samples and get the samples optimized. So we spent actually several years before we could make enough of the parasite actin for all these experiments. So I think we spent probably 2-3 years just trying to get the samples for the measurements. And that's definitely the biggest hurdle, I would say. So when you can make your samples, your biological samples, then it's just to go and measure, and results might be surprising, might be difficult to interpret, but it's fairly easy to get to do the measurements.
Okay, thank you very much to Inari from Norway, and wishing well, of course, for further researches and science. And now we are changing region a bit and going to Russia. And my pleasure to introduce here on the online stage Vadim Parfyonov, who is professor at St. Petersburg Electrotechnical University. So Vadim, the floor is yours.
It is my great pleasure to take the opportunity to join this video conference, and I would like to send you my warmest wishes from St. Petersburg, from cultural capital of Russia. Now, let me start my presentation. Just a moment, please. Just a moment. Okay. Do you see it? Everything is fine?
No. At a particular moment,
okay.
We don't see it, unfortunately. Maybe you can try one more time. Yes, we see your screen, but not presentation.
Just a moment, let me try again.
Mm-hmm. Do you see it now or not? Still we don't see, but we can start presentation from our side here. We have your presentation, so we can put it on the screen, and then you have just to say next slide please, and we will scroll presentation for you.
Do you see my presentation now or not?
No, unfortunately no.
Okay, let's try to use your version of my presentation. Sorry for technical problems.
That's absolutely okay. That's absolutely okay. Then we're gonna put the presentation in our side, and everything will be just fine.
Okay, let's try to do.
Mm-hmm. Okay, for those who are watching us at a particular moment, we are trying to set up presentation, and here it is, and we are ready to start. Mr. Parfyonov, the floor is yours. So we can see the presentation now. Everything is fine.
Okay. Sorry for technical problems again. But anyway, my dear colleagues, today I would like to tell you about very interesting new but rapidly growing field of application of laser techniques, which is connected with the use of laser technologies in cultural heritage preservation. Next slide, please. Okay. I represent St. Petersburg Electrotechnical University, which is one of leading technical universities of Russia. In fact, our university was the first technical university in the world dealing with electrical engineering. It was established more than 100 years ago, and at the moment we have almost 10,000 students. Next slide, please. Sorry, I don't have a feedback. Can you see my presentation now on the screen or not?
We see, everything is fine.
Now the slide is called contents, yes?
Yes, the contents.
Yes, it's correct. So, you can see here the contents of my presentation. In the beginning, I will give you a very brief overview of research activity of my university connected with the use of technology of laser cleaning. Then I will speak about another technology, which is 3D laser scanning, which can be used for documentation, monitoring, and replication of artworks. So, in the beginning, I would like to say that unfortunately, for last several decades, the speed of deterioration of cultural heritage objects, especially cultural heritage objects which are exhibited at the open air conditions, became more high, and now for 2 or maybe 3 decades, we have the same changes in the condition of cultural heritage object, which took place before for several centuries. And very good illustration of this fact you can see here in this slide, where you may see the difference in condition of the same marble sculpture for very short interval of only 50 years. In this situation, there is a strong need in finding advanced and very effective techniques and approaches which can be useful for solution of problem of monitoring, restoration, and analysis of cultural heritage objects. Unfortunately, traditional approaches to cultural heritage preservation now are not so effective, and new solutions are required for effective resolving of current and actual works, problems of modern museum work. And it's very interesting to mention that one of most effective approaches to the solution of above mentioned problems is the use of laser techniques. At the moment, there are at least 3 already established areas of application of laser techniques in cultural heritage preservation, which are listed here. Among them, the restoration of artworks using technology of laser cleaning and laser micro-welding, analysis, structural diagnostics and documentation of artworks, and also there is another application of laser in this field, which is environmental monitoring and monitoring of outdoor and indoor cultural heritage objects. Historically, the first application of lasers was in 1972 in Italy, thanks to pioneering works of American physicist John Asmus, who was first who applied lasers both for documentation, for analysis, and for cleaning of artworks. He applied laser techniques for restoration of some important historical monuments in Italian city Venice. Already 70 years after the first experimental trials of John Asmus, the first very important and large-scale practical restoration project took place in Italy again, and that project was connected with the laser cleaning of the facades of Church Cremona Cathedral in Italy. And those works also Professor Asmus took part, and let me say again that it was first and large-scale restoration project using lasers. At the moment, if we will take a retrospective view on the history of use of lasers in cultural heritage preservation, we can say that nowadays lasers became a routine tool in hands of many restorers and curators in many museums around the world, and there are a lot of very amazing case studies concerned with the use of lasers for restoration and for analysis and documentation of work of arts around the world. Among them, in particular, the cleaning of the bas reliefs of Parthenon in Greece. Also, one can mention that lasers are used on the routine basis in the British Museum, in the Louvre Museum, in Metropolitan Museum, and many, many other museums around the world. Speaking about usage of analytical techniques, I can say that today one of mostly frequently used laser techniques for documentation of artworks is 3D laser scanning technology, which also was applied for analysis and documentation of many very important cultural heritage objects around the world, including some historical monuments and also paintings and other works of art. Also, there are many analytical techniques for analysis of artworks, and among them there are, for instance, some laser spectroscopic techniques which are listed here, and one of most frequently used analytical techniques is so-called LIBS, which does mean laser-induced breakdown spectroscopy. This is very useful technique which makes possible the analysis of chemical composition of artworks and deterioration layers on the surface of cultural heritage objects. And for instance, this technique is very frequently used for identification of pigments in paintings. So this is a brief general panorama connected with the use of laser techniques around the world. But now I would like to switch your attention to research and practical works of my university. At St. Petersburg State Electrotechnical University, there is a research and educational laboratory for laser technology of analysis and restoration of artworks, which is based at the Department of Photonics of my university. This laboratory consists mainly from young scientists, students, and PhD students. And though the number of persons working at the laboratory is not so high, we are only about 10 persons, we were very active for last several years, and we took part in many important projects in collaboration with leading museums of St. Petersburg and Moscow. And now I would like to give you a brief overview of our research and practical activity. Speaking about the main fields of our work, I would like to say that we do deal with laser cleaning of stone, paper, and other organic materials. We also do DEVIL analysis of paintings by means of use of laser spectroscopic techniques. And one more field of mainly our research activity is the solution of problem of inactivation and removal of biological growth, I mean films of microorganisms from the surface of cultural heritage objects. And also we do deal with study of accuracy of creation of computing 3D models and accuracy of replication of artworks in case of use of 3D laser scanning and optical scanning technologies for documentation and replication of artworks. Now very briefly about our works concerned with laser cleaning. Firstly, let me very briefly say about physical principle of laser cleaning. For instance, here we can see the cross-section of stone monuments. For instance, it can be marble. Usually on the surface of outdoor cultural heritage objects, there are different kinds of deterioration layers. For instance, some black crust films, biological growth can occur on the surface of historical monuments. And in the process of any restoration, it is necessary to remove by very delicate way the deteriorated layers. The contaminants must be removed safely. And laser can be very effective in the solution of this problem. If we will irradiate the surface of monuments by intensive laser beam, due to the inactivation of the process of photoablation, and thanks to creation of mechanical stress waves, we will be able to remove by means of ejection of dot particles, we will be able to remove all contaminants from the surface of artwork. It's very important to note that this process can be self-limited, because as soon as laser beam will achieve the surface of monument, all light of laser will be reflected by the surface of historical monument. Of course, only in that case, if we will be able to choose the parameters of laser by a proper way. And the necessity to find the optimal parameters of laser radiation in case of restoration of particular specific artworks is a serious subject of research works, and exactly taking into account the necessity to resolve this problem, we were working already for at least 15 years on optimization of processes of laser cleaning of different artworks. Now, a few case studies connected with our practical works. As I already mentioned it before, we have a very fruitful collaboration with some leading Russian museums, including, for instance, State Russian Museum, which in fact is the Museum of Fine Arts of Russia. This museum has the best collection of Italian sculptures of ancient century, about 100 sculptures created by very famous artists of Italy. And here you can see the typical deterioration problems of these sculptures before restoration, and the process of restoration work, which have been carried out in collaboration with restorers of the State Russian Museums. My laboratory successfully did clean 32 sculptures using technology of laser cleaning. Here is one more case study connected with our collaboration with another museum in St. Petersburg. This is Museum Tsarskoye Selo, and here you can see the initial condition of one of marble sculptures before in the process and after finishing the laser cleaning of the sculpture. There is one more case study. You also can see the effective result of cleaning, of removal of different contaminants from the surface of the sculpture. So as you can see, we're really very active in the field of laser cleaning. But from scientific point of view, as I already mentioned, it is very important in each concrete case, for each concrete monument, to find the optimal parameters of laser radiation. And for instance, here I tried to summarize the most important parameters which were optimized in the framework of research works of my laboratory. For many years, we also very active in the solution of problem of removal and inactivation of biological growth, which very frequently there is in the surface of many artworks, not only outdoor sculptures, but also this is a problem of paintings, books and documents in many museums and archives around the world. And using laser, as we did show, it is possible to very effectively inactivate and removal without any damages of surface of artworks and other historical objects, biological growth using, as I already said, using lasers. Now about our activity in the field of laser 3D scanning. This technology can be very effectively used for documentation, monitoring and replication of artworks. I hope that everybody knows a lot about advances of laser 3D scanning technology, because using laser it is possible to create precise virtual copies of any objects, including artworks. Using 3D laser scanning technology, one can create detailed, very precise 3D models of cultural heritage object. But what is very, very important, laser 3D scanning technology not only reproduce the image, 3D image of cultural heritage object. The use of this technology make possible to measure sizes of cultural heritage objects, and also one can analyze any defects, for instance, cracks, the biodeterioration and other problems with erosion of surface of cultural heritage objects. For this reason, this technology now is very frequently used for documentation of artworks. And we took part in many practical works using this technology in collaboration with many museums in my country. And we also do use this technology for non-contact replication of cultural heritage object, especially heritage object which exhibited at the open air condition, because at the moment there is a very actual task in the change of highly deteriorated sculptures and other historical monuments by means of the replication by replicas. So, using 3D scanning technology, this work can be done by a very effective way, because 3D laser scanning technology can be combined with the use of CNC machine milling technology or with the use of 3D printing. And using this approach, one can create very precise copies of historical monuments using original historical material. For instance, marble sculptures can be replicated using marble, and other monuments also can be replicated using original historical materials. So it was, from point of view practicability of this technology, but I would like to pay your attention that there are a lot of very serious scientific issues concerned with the use of 3D laser scanning for replication of artworks, because at the moment the problem of investigation of accuracy of creation of 3D models of cultural heritage objects and the problem of precision of replication is not enough good studied. For this reason, there is an open air for study of these issues, and my research group is very active in this field. So, very briefly, in the final part of my presentation about possibility to use 3D laser scanning technology for monitoring of artworks. 3D laser scanning can be applied for precise analysis of defects of erosion of surface of outdoor monuments, but also it can be applied for monitoring of paintings, for instance, tempera and oil paintings. And here is one of case studies connected with works of my group. We collaborated with one of museums in St. Petersburg in monitoring of paintings. And if we will repeat 3D laser scanning, and if we will match obtained 3D models taken with some time interval, for instance, 1 year, 2 years, 3 years, it is possible to get information about creation of some defects, about deformation of canvas, about problems, about defects of wooden frames of artworks, etc., etc., etc. So, as you can see, this field connected with the use of laser technique has a very interesting perspective, and this is a field where a wide collaboration of different research groups around the world, around the Europe, can be realized. And speaking about some kinds of possible international collaboration under auspices of the Baltic Science Network, I would like to say that we can try establish joint research projects. Also, we can speak about possibility to arrange the exchange of students, PhD students, and research staff. And here you can see only a few areas, concrete, specific areas of possible collaboration. So we are open for collaboration. We will be waiting for some initiatives from our partners, our colleagues around the Baltic countries. And here, very briefly, the last thing about which I would like to tell you today, just for your information, I am pleased to say that in this year, my university opened a new international language English language Master of Science program, which is called Heritage Science. And this program combines knowledge and engineering and humanitarian science for resolving the most actual tasks of cultural heritage preservation. And I'm pleased to say that our university is only one in Russia and one among a few universities around the world which has such Master of Science program dealing with cultural heritage preservation, where, for instance, knowledge and experience in laser physics, laser technology can be used. So, possible kinds of collaboration here, of course, mainly academics. We can, I hope, agree about internship of students and PhD students, and of course, the program of so-called double diplomas also can be realized. So, it's all what I wanted to tell you today. I hope this information was interesting and useful, and I would like to thank you very much for your kind attention. Thank you again.
Thank you to Professor Parfionov, and indeed a very visually impressive presentation. Thank you very much for that. And we have also a couple of questions for you, Professor. The one is, could you comment on availability and cost of this technology if we are looking from museum perspective, how available this technology is, for instance, in Russia, and how costly it is you can mention your examples, but for instance, to scan one monument for restoration. So the cost and availability.
Of course, the use of lasers is expensive approach, but I can say that any restoration, any documentation of artworks is always expensive too. But if we will compare the cost of the use of laser techniques, for instance, for cleaning, and if we will compare the cost of replication of artworks using combination of 3D laser scanning and CNC milling machines, you will be surprised that the cost of laser-based approach in comparison with conventional approach is approximately the same. So the use of lasers not much expensive. This is a competitive, absolutely competitive with the use of traditional techniques for restoration and documentation and replication of artworks. If we will speak about practicability of use of lasers, I can say that in Russia, laser techniques are not so frequently used at the moment, but at least some leading Russian museum, for instance, the Hermitage Museum, the Museum, State Russian Museum, which is in fact is the Museum of Fine Arts in Russia, already have some laser tools. I mean lasers for cleaning of artworks, lasers for analysis and documentation of artworks. So laser techniques expensive, let me repeat once again, but they are already available in the museum community in Russia.
Thank you very much for your answer. Then we have a very interesting question, but I believe only you, Professor, can answer that. How do you see the future of museums in 20 years, taking into account that you were telling that there are possibilities for making replications in 3D, and there are possibilities to clean cultural heritage. So the question is, what will be in the museums, originals or replicas, taking into account the progress of technology in some next 20, 25 years?
This is an interesting and very frequently debated question. My personal opinion that, of course, use of advanced techniques is only a good addition to the usage of traditional approaches in the museum works. Of course, it's absolutely impossible to change the original artworks by copies. The replication of artworks now is actual only for those cultural heritage objects which are exhibited at the open air condition, and only for those cultural heritage objects which are really highly deteriorated and which really do need in replication. In the meantime, let me say that replica don't exclude the value of original artworks. Replica is placed on the site of location of original, but original artworks can be moved to the museum and real and people which are really interested in artworks always will be able to go to museum to take a look on the originals. original artworks. Another matter that the use of 3D laser scanning technology may make possible the higher availability of artworks for many people. For instance, for people which are not able to visit some museum in abroad. If we will put in the virtual space some virtual copies of most important of artworks, it will make the availability of at least virtual copies of artworks more useful for many people. So for this reason, new technologies, for instance, new approaches based on the use of laser techniques can make more interesting possibilities for people. But let me repeat once again, but it's of course only my personal opinion, that any new techniques and possibilities provided by advanced techniques will never change the value of real artworks. So this is my question on your answer. My answer on your question, sorry.
Thank you very much, Professor. And really, indeed, there are things to think about considering future. I remember there was an author, Stanislav Lem, who was writing about the cultural heritage in the future, and that was in the last century, 20th century, and now the future is already here with the making 3D replicas. Speaking on Stanislav Lem, he was from Poland, and our next speaker is from Poland, and my pleasure to invite here on our online stage at this particular moment, Joanna Kapla-Masztafiak, Assistant Professor, Institute of Nuclear Physics, Polish Academy of Sciences, Krakow, Poland. And Joanna is going to speak on complementary use of laboratory and free electron X-ray sources to study metal-based complexes. So we are full attention to you. Joanna, the floor is yours.
Okay, can you hear me?
Yes, we hear you absolutely wonderfully.
And you can see my presentation also?
Yeah, either.
Okay, thank you very much. Good afternoon. Thank you very much for the invitation and thank you very much for the introduction. I will tell a little bit about our research with the use of laboratory and free electron X-ray sources to study metal-based complexes. I'm representing the Department of Applied Spectroscopy of the Institute of Nuclear Physics, Polish Academy of Sciences, where we use X-ray spectroscopy to study biological samples, like, for example, DNA and the interaction of metal centers molecules with some biomaterial. But we also study the chemical systems, for example, charge transfer processes, and also some fundamental physics research like nonlinear interactions are also studied. We use all kinds of X-ray instruments. For example, laboratory X-ray spectrometers, synchrotron sources, but also free electron lasers. And next to the application of these sources, we also develop some new instruments, absorption and emission spectrometers, sample delivery systems, and so on. So this is what we do. And now, firstly, I will show you about our laboratory spectrometer. This is a new instrument that started its work a year ago. As you all probably imagine, that was a very hard year for us, but we still managed to do some commissioning and start some scientific project on this instrument. Here is a general scheme of the setup. So the design is constructed the way that you can do absorption and emission simultaneously. It is based on two von Hammer's spectrometers with 2 diffracting crystals and 2 CCD cameras. Here you can see the picture of the instrument during the operation. This is the absorption spectroscopy experiment with X-ray tube with polycapillary. Here is the sample holder. So the X-rays go through the sample, they are diffracted by the crystal and analyzed by the CCD camera. And here is the second CCD camera ready for the emission spectroscopy studies. So here are some preliminary results from the measurements of solid samples. This is the iron K-beta emission and iron KH absorption. 2 acquisition times are visible here on the spectra. As you can see, after 20 hours, so in general, after 1 day of measurements, we get a very smooth, very nice spectrum with all the features visible, and even with these details that are not so intense, you can distinguish all of them. But in biological studies, that is my main field of interest, and in chemical studies, we want to study liquids. So we also develop a liquid sample delivery system that was developed by our now PhD student during his master thesis. This is a very nice design with a quartz cuvette cut by half, and you can measure also liquid samples in a liquid jet, let's say. Here are the results. So the spectrum from zinc oxide in a liquid form studied in our lab is compared with the synchrotron data and with theoretical calculation. So you can see that the shape is pretty much the same, and you can also distinguish all of the details and all of the features that are important during the analysis of the absorption spectra. So that was the commissioning, but we also started some scientific project already. And one of them is the project that is funded by National Science Center in Poland, the studies on the interaction of copper-based complexes with DNA by means of X-ray spectroscopy techniques. Why do we want to study these complexes? Because there are some limitations of the popular chemotherapeutics that are used nowadays, for example, cisplatin. Cisplatin is highly toxic, so it gives a very severe side effects. But also we observe some primary or acquired resistance to this drug. So it is important to develop new compounds. They can contain platinum, but platinum is quite expensive, so we are also looking for other elements, like, for example, copper. What we are studying is a set of copper and phenanthroline-based complexes with different structures. And if we study new compound in terms of potential chemotherapy, we want to know if it is cytotoxic, so if it kills cells, but we also want to know what is the mechanism of action and what is the link between the mechanism of action, the activity, and the structure. So these are the chemical information that we can get from X-ray absorption. And here are some preliminary studies. That was also a master thesis of my now PhD student. Here are the spectra, the absorption spectra of different copper samples, among them the phenanthroline copper complex. So you can see that with the laboratory source, in laboratory condition, you can easily distinguish the oxidation state of the compound. You can also see very nice shape of the spectrum, so you can tell something about the chemical structure. And if you combine this with theoretical calculation, you can get the information about the electronic structure, so about the density of states. What are our future perspectives? We would like to, of course, do simultaneous absorption and emission experiments of our biosamples. We would like to study biological samples in a liquid form. This is quite important, but these samples are usually in very low concentration, so this is quite a challenge. And actually, this week, these measurements are performed, so we hope that we will get into very low concentration of the samples. And we also like to have a biolab on site, so we can study not only the interaction of drugs with DNA, but also the interaction of drugs with living cells. And here I will show you the example of our studies done on free electron laser. So free electron lasers can be used for mainly for three types of experiments. Single-shot experiments where you need lots of photons in a very short pulse. The pump probe experiments where the short pulse allows us to measure fast processes, and also in a non-linear X-ray experiments. So this is types of experiments where you can really benefit from using free electron laser. And of course, during these experiments and during all experiments with hard X-ray, you can expect some radiation damage of your sample. To some extent, every sample is damaged by X-rays. Of course, we know how to reduce this effect now. We can use liquid jets, sample circulation, cryocooling techniques, or in case of XFEL, we can do the experiments in a probe before destroy methodology. So the challenge of X-ray radiation damage is well recognized, but rarely studied systematically. So our experiment was performed on the linear coherent light source at the XPP station with the above iron K edge. We measured X-ray emission signal also with von Hammes spectrometer on the hexacyanoferrate sample in an aqueous solution. So that was our sample. The pulse length was 30 femtoseconds. These are the experimental conditions. And what we get, so our signal, it turns out that our signal is changing monotically with the increased photon flux. So that was the observation. And we start analyzing these results. We started with analyzing photon absorption of this solution. It turns out that most of the events result in oxygen photoionization in the solvent. So based on energy and time-dependent calculation on electron interactions, it was proposed that after the X-ray radiation goes in, it interacts with the solvent. Then there is a generation of energetic electrons, and then these electrons impact iron ionization. So it is a, you can say, three-step process. And then what we get is a signal of the iron K-beta emission. So in the time of 13 femtoseconds, we get a highly charged state molecule, but with preserved atomic position. So to sum up this experiment, excuse me, we can say that these X-ray photons induce solvent ionization firstly, and leading to the formation of the electrons, and these electrons reach the nearest iron atoms in less than 1 femtosecond, and this leads to the ionization and increased iron oxidation state, but without affecting molecules' atomic position. This is a very important result in terms of performing experiments on samples embedded in solution or in matrices, because you always need to think not only about the interaction of X-rays with your studied complex, but also with the solvent. So what about this complementarity? There are many advantages of using laboratory setups and free electron lasers, of course, but if we think about it as a whole, we can say that in case of laboratory setup, we have a constant access at home institution usually. This was very important before, because the time from the application for the beam time and to the experiment was quite long. But now it is even more important because if you can go abroad or you need to stay at your institute, you still have an access to the experiment. But with the laboratory setup, you can make a principal analysis, so the chemical structure, the oxidation state of your sample, and also the electronic structure of the complexes. And in case of the processes, you can define the initial and final state. And what was also mentioned today, it is important to make a very careful feasibility studies. So this can be done at the laboratory setup. And in case of free electron lasers, of course, they have a unique X-ray properties and exceptional temporal resolution. So we can study the phenomena that are unavailable to study with the conventional sources. And so to sum up, using both approaches gives us the opportunity of this detailed sample analysis. And of course, I would like to acknowledge a few institutions that were involved in these studies. And I would like to thank you for your attention, and I'm happy to answer your questions.
Thank you very much, Giovanna, and thank you also for the pictures in the presentation to get the full scope and the sense of science in your country. And the question is, you mentioned that the time is pretty long from application until the experiment within the home institution. Then the question is, could you comment on the timetable from applications till experiments overall?
So what I mean by this time was the application for the beam time at the central facilities. So at the synchrotron and at the free electron lasers. That was already mentioned today, that it is about sometimes even 9 months of waiting from your proposal to the experiment. In the case of laboratory setup, of course, we also have a timetable in our lab, but this is usually within few days, or in the worst case, a week, let's say.
You mentioned a lot of bonuses and pluses to laboratory setup, the home institution. Are there some negatives or minuses to this?
Yes, of course, the minus for sure is that you can study very, very low concentrations. And sometimes if you have very small amount of your sample, it is difficult to, for example, in case of liquid sample, to get a lot of solution with high concentration. So that's the main minus, I would say.
Okay, thank you very much, and wishing you luck in future researches, Giovanna. Thank you. And we are moving now to neighbor country of Latvia, Estonia, and we're gonna see the presenter, research professor in biophysics, University of Tartu, Jorga Piper, and he gonna tell us insights into solution structures and dynamics of biomolecules provided by neutron scattering techniques. So Jorg, the floor is yours, and we are happy to have you here.
Thank you very much for the nice introduction. I'm very glad to speak at this interesting meeting and to introduce some of our work on structure and dynamics of biomolecules, studied mainly with neutron scattering, but also with X-rays a little bit. This is mainly work done with my postdoc Maxime Golub and me, but to have a short outline, I will have two basic parts of my talk. The first part will deal with solution structures studied by small angle scattering methods, and the second smaller part will deal with molecular dynamics studied by neutron spectroscopy. And at the very beginning, I want to acknowledge, or at least show you, that many people across Europe have been involved in this work. And I also want to thank the scattering centers ILL, MLZ in München, Germany, and FLNT in Dubna, Russia, for providing beam time and for providing support for our experiments. And to come back to the outline for the work on solution structures, I don't want to go into too much theoretical detail, but I will hopefully show you some instructive examples of what you can really do with these low resolution structural methods. And the four basic aspects are studies of oligomerization state of biomolecules, complex formation of biomolecules, then the study of detergent shells or solubilization of membrane proteins, and finally light-induced structures that can, structures that can be induced with external triggers. To introduce the sample systems to you, the first is a protein called phycocyanin, this nicely donut-shaped structure that you see here, which is a light-harvesting protein in cyanobacteria. The second is so-called photosystem 2, which is capable of splitting water into hydrogen and oxygen. So this protein is responsible for the oxygenic atmosphere that we have. But you can imagine that at the moment there is a technological interest in this protein because it may teach us how to produce hydrogen from light. And finally, I will speak about the orange carotenoid protein, which is active in photoprotection of light harvesting systems. Well, you may ask, I show you here very nice high resolution crystal structures. So you could say all the structural questions are solved. Why do we need low resolution methods to study such systems? And there is one basic reason and several particulars that apply to each system individually. But the basic reason is that functional studies on proteins are often performed in solution, in aqueous solution, which is closer to the native state of the sample. So in principle, one needs to prove that crystal structure also applies for the solved sample. And if we go into the detail for each of the sample systems that I want to introduce to you, then phycocyanin has the property to occur in different oligomers, and depending on organism, it may form various supercomplexes. So, which are not all crystallized, so that low resolution methods can be very instructive for such studies. then the photosystem 2 is a membrane protein, and to isolate such a protein for functional studies requires the use of detergent molecules so that it can be isolated in aqueous solution, which makes it a more complicated problem. And finally, the orange carotenoid protein is very interesting because the crystallized structure applies to the dark inactive state, while the active state has to be induced by light. It is not crystallized at all, so that low resolution methods are very powerful in this case. So what I would like to show you in my presentation is that small angle scattering methods can deliver structures in buffer solution under the same conditions that are used for experiments on protein function, so that structure and function can be directly correlated. But let's start with the first two examples, oligomerization and complex formation. And I use phycocyanine as an example. You see here it can occur as a hexamer or a trimer. That means if you study your solution by SAX, you get green points, and advanced simulation tools that are available from the group of Svergun at DESY in Hamburg allow us to calculate the scattering curves directly from the PDB codes of these crystal structures, and you see that the curve of the trimer fits our data much better than the hexamer. So most probably we have a trimeric sample here. And there is another software tool that allows you to reconstruct the solution structure from the SAX data and likewise from the SUNS data. You see this as gray spheres superimposed on the trimer structure. And this gives you a quite nice feeling for the uncertainty or capability of determining size and shape of a biomolecule with small angle scattering methods. So here for our sample, we can rule out the hexamer structure. But what can we contribute to the question of the supercomplex that phycocyanine forms? In usual cyanobacteria, you see the structure on the left side of the slide, which is very complex. You have several rods radiating from a central core. And we studied a system from a particular cyanobacterium called Acariochlorus marina, which is supposed to form a rod-shaped supercomplex of phycocyanines. But it was unclear under which buffer conditions do you really retain such a structure, and how many phycocyanine subunits do you really have in this? So we performed experiments on these phycobiliproteins in phosphate-containing and phosphate-less buffers. You see the phosphate-containing sample as blue points in the slide. And this can be nicely described simply by a cylinder model with a length of about 225 angstrom. So for this buffer condition, we can prove that there is a rod-shaped assembly, a cylinder shape, while if we move to the phosphate-less buffer, then this structure seems to be lost, and the cylinder model still applies, but the height of the cylinder is only 28 angstrom anymore. And in addition, you see that for small scattering vectors Q, there is a huge increase in the signal, which usually indicates unspecific aggregation. So we have more or less the same sample in two different buffer conditions, but the structures we get are completely different. And without a small angle scattering study, you wouldn't have noticed that. You would have compared with the crystal structure that probably does not apply. And with this structural information, you can also explain why the function of the phosphate lacking sample is impaired, because simply the active structure is split into pieces. That is summarized on this slide here. For the phosphate containing sample, we get a cylinder shape that contains 8 subunits, while for the phosphate-less sample, we get non-functioning materials which are split into trimeric phycocyanine subunits and which show unspecific aggregation. Now with that knowledge, we can move to the more complex situation of membrane proteins. And here I show you the structure of photosystem 2 and the structure reconstituted from a small angle experiment as gray spheres superimposed on each other. And you see they seem to nicely fit, while the sphere structure is a bit expanded. So it might be that in solution this complex is a little bit larger. But after my introduction, you may miss the detergent belt around this membrane protein. And why we don't see it, the reason is that we have a so-called contrast matching technique here, which is only available in small angle neutron scattering. And the principle of this is outlined on this slide. You see we have a 3-component system, the protein in blue in the center, surrounded by an orange detergent belt, and this again surrounded by the solvent. And particularly using neutrons, we have the possibility of contrast variation when we use or when we vary the content of D2O and H2O in our solvent, because neutrons are sensitive for isotopes. They study nuclei, and this means we can we can vary the scattering properties of the solvent, and we find so-called match points where the scattering property of the solvent matches that of the detergent belt, while in the second case the scattering properties of the detergent are not matched. So we can do small angle neutron scattering under matching and non-matching conditions for the detergent belt. And this slide shows you the differences in the results that you get and in the data. In the first case, with 5% D2O in the solvent, we match the hydrophobic chains of the detergent molecules, which means we selectively see the protein, while in the second experiment with 100% D2O or with small angle X-ray scattering, we see the envelope of the protein with its detergent belt, and we can model a monomolecular belt of detergent molecules around the photosystem. Please note that the protein with detergent belt is the top view, while the protein selectively measured is the side view. So this is a bit probably. But to summarize this subpart, we can measure the photosystem 2 solution structure by small angle neutron scattering with contrast variation, which is very close to the X-ray structure, but seems to be a bit expanded. And especially we can detect a monomolecular detergent layer around the molecule when we use non-matching conditions. So to move to the last example for small angle scattering, the light-induced structures, here we study a protein where only the dark ground state is crystallized, but if the molecule has to become functional, you have to activate it with light, and then its 2 domains seem to split before they can bind to phycobilly proteins. And we are interested in this first step here that can be induced with 480 nanometer blue light. This means we have to interface this light excitation with the small angle experiment here shown for an instrument at MLZ München in Germany, where you see our illuminated sample container, and it's not sufficient only to illuminate, but you really have to make sure that your sample is really converted more or less completely to the active state. And you see this here in the right lower corner, where an unilluminated part of the sample remains orange as in the ground state, and the illuminated part becomes red. Then we get really two distinct small angle curves for the dark and for the illuminated sample. And the dark sample nicely fits with the dimeric ground state crystal structure, while the active state structure appears to be expanded. And you can model the separation of the two domains with software tools available from the Dimitri Svergun's group at DESY. So to summarize this part, we managed to convert OCP to its active state under illumination, and we can see a domain separation with this experiment, so we can well characterize the active state. Summarize again, for the small angle part, we can check oligomerization and aggregation. We can test complex formation from systems with known crystal structures. We can determine solution structures at physiological conditions, and even follow conformational changes on external triggers. The second shorter part is about molecular dynamics, because once we see these beautiful pictures from crystal structures, one often forgets that the proteins are rather flexible entities. And to illustrate that, I want to show you a molecular dynamic simulation that I can show you courtesy of Dr. Byers from University of California. And this movie nicely shows you that a protein is a very dynamic entity, and smaller residues are moving on picosecond timescale. We have measured that for photosystem 2 and expressed this flexibility in terms of a mean square displacement. You see here in this slide at low temperature, this displacement is rather small, but towards physiological temperatures, it increases a lot. So especially for physiological processes, we have to keep in mind that flexibility is important, but we do not see so much flexibility in the dry state. So hydration of the molecule seems to play a role, and for that, I switch on the video once more and tell you that the dark gray is the protein itself, while the light gray red molecules are the water molecules that are wiggling on the surface of the protein and are initiating the motions of the protein. And you see that with our neutron spectroscopy, you can measure these displacements. Why is this important? Here you see the curve from neutron spectroscopy superimposed with a measurement of electron transfer efficiency, and you see that the two correlate. So there are functional processes in photosystem 2 that seem to require flexibility, and there are several structural models that show us or that give us an idea which smaller conformational changes in the photosystem 2 may require conformational flexibility. And very finally, I show you that we are setting up experiments for time resolved studies of dynamics of biomolecules, here shown for the example of bacteriorhodopsin, where you can initiate its function also by a light quantum. Then it undergoes a photocycle through several structural intermediates. And if you interface a neutron spectroscopy experiment with external illumination, you can, instead of a snapshot of the dynamics, in principle measure the movie through all these functional states. And this is what we have here. So to conclude the subsection, probe neutron experiments can be performed, but they require a lot of neutron flux and they permit preparation of specific functional states and their characterization, but they highlight the active role of dynamics in functional. And with this, I want to thank all co-workers for the particular projects that I have introduced here, and I thank you for your attention.
Thank you very much, Jörg. And we have indeed many questions because of such an insightful presentation. The question is, for your study, did you use the same proposal to get the beam time at synchrotron and at a neutron facility? And if it was in the sequence, did you use the fact that you had the BT in either in a SRS or a neutron facility? I hope you understood the question.
Yes, but this, of course, this is a very important practical question, but this varies from project to project. And as we have also seen in the talk before, sometimes it's good if you can perform some of your experiments in a laboratory where you have easy access and you can try out things and you can do feasibility studies. But of course, then it's also important to apply for large-scale facilities because you get higher flux. You can study samples with smaller amounts and smaller concentrations. And especially because I feel an interest in combining SUNS and SACs from this question, there are centers like ILL and ESRF who provide the opportunity to apply for both SUNS and SACs beam time at the same time. You submit one proposal and you can pick an option, and once your SUNS proposal is accepted, you get automatic beam time at ESRF for SACs experiments. And especially the Photosystem 2 study was done in this way, and it turned out to be a really nice combination of complementary methods.
Okay, so you did that in a complementary way. The next question is classical, and this is so specific that only you can understand that, I believe. Classical MD potentials may perform poorly when van der Waals interactions are present. How was the MD potential tested?
For this particular movie that I can show you, I cannot even answer this. I would have to direct this question to Doug because this is not my work. I have shown it for illustration purpose. We are at the moment moving into this direction because I think it is a crucial combination to combine MD with the experimental neutron spectroscopy, simply because MD gives you a better idea of a structural assignment of the motions that you see. So I'm sorry that I can answer this question only in general and not in particular.
But definitely we're going to address this question particularly after the conference and find the answer for those who are asking this question. Then the next question is about team of authors. At the beginning of your presentation, you showed how many people are behind the research from many countries. And the question is, what does it take to be in such teams and to organize such teams? That's a very human question from everyday's perspective. What does it mean to be a part of something and also organizing something?
Yes, I would say that work on such a complex scientific question requires teamwork to begin with. There is almost nothing that an individual person can do by himself or herself. And of course, all these people that you can see who have contributed in many different ways. First, when you apply for beam time to a scattering center, you get a local contact. And this is a scientist that constantly maintains an instrument and upgrades this instrument to the best standard. And without this basic work of this local contact at the scattering center, a scientist who is just a guest there could not do anything. So this is the local contact at the scattering center is, of course, a very important contributor to such a project. And once you combine SUNS and SACs, you already have at least 2 contacts in the centers. Then, of course, we work with people who have all the knowledge on biochemistry, who know how to extract an isolated photosystem from a membrane and from a plant or from a bacterium, which we as physicists couldn't do. And so all such contributors or collaborators you need to successfully perform such a study.
Okay, thank you. And then at the beginning of afternoon session, there was mentioned the huge role of modeling before going to real experiment. Could you evaluate a bit the stage of modeling, how much time it takes, and what's the reality behind the modeling in a research?
Yes, actually that is a 2-stage process, because a collaborator may turn to you and say, we have an interesting protein, it would fit into our field of collaboration. Can we do a study? Can we apply for beam time somewhere? Then it means you have to analyze the system first and, for instance, check out how large will it be? Which structure do you have to expect? And as I mentioned in one of my slides, from a structure that we expect, we can already calculate a model curve, and this defines the experimental conditions that we have to ask for at a particular scattering center. So when we write our proposal, we should already know roughly what size of protein, what shape of protein should we study, or in these studies with external triggers, which changes do we really expect? And then we can define the experimental conditions and ask for experimental conditions in a more elaborate way. And then, of course, once we have done our experiment and we go home with the data to our home institution in Estonia, then the real work starts for us, because then we have to model and find out which shapes, which conformational changes have we really seen in our experiments. And this can take a long time.
Okay, thank you. And then the final question, which is a very, very human type of question. What would be your advice from Tartu to your colleagues in Riga?
That's a very good question. I would say take the opportunity that is offered by such nice events as you have organized and form collaborations, because as you say, the author lists on our project proves collaboration is the key to everything.
Thank you. Collaboration is the key for everything. That will be definitely one of the, I believe, conclusions of this conference. Thank you, Jörg, very much for this intense Q&A session, and wishing you well, of course, in the further researches and studies. Well, now we are coming closer to the final speaker of this day. Before that, keeping up the tradition, before the final speaker, we are informing you, because after the final speaker, everyone gonna run away. survey. So we are informing about that now, that we have to give the feedback of conference, and we are starting to give the feedback already now. So, ladies and gentlemen, those who are watching us, you already recognize this beautiful square. This is QR code, and the QR code will lead you to the feedback survey of this conference. And this time we made it a bit more easy. The 5 is good, the 1 is bad. So that's the main idea. The 5 is the good wing. The 1 is the bad wing. So the higher the scores you put, the better. So definitely you can follow the QR code, or if you are not in QR codes, then you can do that in a good old-fashioned way. Use the code which is in the left side of the screen down there, 9670848. So that's what you can do. So now is the moment when you're doing that. Now is the moment when you are doing that. You are opening up the feedback survey and starting to fill in your perspective, because that's extremely important for the organizers of the conference to proceed with such a conferences in the future, and of course to proceed even in the next level of excellence and the quality, considering the organization, reachability, accessibility, and other fields which are asked in the survey. Definitely feel free to show your thoughts, and the more critical they will be, the more objective they will be. So feel free and fill the survey of our feedback. Just for sake of feeling, this day was pretty intense and pretty long, and in the first part of the day, in the pre-afternoon session, we were discussing the infrastructures, showing the different examples of infrastructures all around Europe and Russia, and how those infrastructures are giving possibilities. That was the topic for afternoon session, where we are speaking and are still speaking on the contents of particular researchers and particular scientists who are using photons and neutrons and electrons in all this field, just to make the common projects and common development. So please leave your votes. That's what now is happening. Votes, yes, like in election. Leave your votes, leave your feedback. That's what the game is now about. We are taking the feedback break before the final speaker. So please fill the feedback, and we will really appreciate that. All the questions that are in the survey are the questions you have to answer. Very good, doing the feedback stuff, and taking some 30 seconds, and if you are not finished with the feedback, then you will be able to finish this a bit later. And yes, the time is now to give the full attention to our final speaker of this day, professor from Technical University of Denmark, who's going to speak on XFELs as a molecular movie cameras, Martin Midom Nielsen. Martin, the floor is yours. We are extremely happy to have you here, and we are giving full attention to you right now. The floor is yours.
Thank you very much. It's a great pleasure for me to be able to be here today, and thank you also for accommodating my somewhat strange schedule in connection with this meeting. Today I have the pleasure of telling you about some of the work we have done using X-ray free electron lasers, and how we can use these wonderful machines as molecular movie cameras. I'm from the Technical University of Denmark, and I have two close colleagues, Christopher Hedrup and Klaus Møller, who has been part in all the work here that I will show you today. So today I will tell you about why do we need to consider specific length and timescales for functional materials, and how can we realize these at using XFELs, and how can we then how can we turn these questions into something that can be answered by using a so-called optical pump X-ray probe techniques. That means that we will be looking at different signals, so we see signals that are encoding the changes in the electronic and geometric structure of the materials that we are studying. And I will also have a short detour in how can we obtain structural information without crystals. And then I will show you an example where we have looked at a donor acceptor system consisting of a ruthenium and a cobalt complex, how we can use our techniques to map the coherent structural changes that accompany charge transfer reactions, and how this may be interesting to elucidate new materials. So the timescales for a functional material depends on the processes that we will study in these materials. And for example, if we shine light onto a ruthenium center here at a functional molecule, then we expel an electron from the ruthenium, and it will go up and sit in the ligand structure around it. So this could, for example, be the excitation dynamics. This occurs on a sub-100 femtosecond timescale. And then afterwards, the ligands may respond to the changing electronic state. This happens maybe at hundreds of femtosecond timescale. And eventually, these changes then leads to a structure in the excited state, and then the electron can be transported out into the electrode and drive a current that can then be used to generate electricity. And this all happens in the sub-100 picosecond timescale. And eventually, around the 100 picosecond timescale, the energy is then released into the environment. And we can track all these processes using an optical pump X-ray probe scheme. So, and again, you can say if your processes are occurring at a very short time, typically the length scales are also rather short. So these are the length scales corresponding to the atomic and molecular length scales. And that means that the area that we need to probe is of the order of 0.01 to 10 nanometers, and the time scales around 10 femtoseconds to 100 picoseconds. This we can obtain using free electron X-ray lasers. They are special in the way that they can produce short and intense X-ray pulses. I believe you have maybe already heard something about free electron lasers earlier today. So I'll just very briefly summarize the key features here, namely that we can, in the 100 femtosecond, we can pack basically the same power that a synchrotron does in 1 second. So this high peak brilliance, where we have many photons per time on the SAM, can give us up to 10 to the 20 watts per square centimeter. And at the same time, the pulses are ultra short, which means that we have the possibility of tracking these processes on the natural timescale. Of course, the further property of free electron lasers is that they can create coherent X-ray beams. We don't use that explicitly in what we do, but it creates potential for future studies where we could use the coherence effect to make imaging on the atomic scale. And just to compare it with the synchrotrons, you see here that the peak brilliance of the free electron lasers is about the same jump as we had from when we went from X-ray tubes to synchrotrons, as we now have from synchrotrons to free electron X-ray lasers. So the increase in power here is opening a completely new land that enables us to do this kind of research. And I just show you here the example of the European XFEL in Hamburg, which I'm particularly attached to. And to achieve this performance requires really big and extraordinary machines. In this case, it's 3.4 kilometers of science basically underneath Hamburg. So how do we do it? How can we use the ultra short pulses to capture ultra fast processes? Well, basically it's shown here in this little animation that with a laser pulse, we start a reaction in our material, and then we can time a delay a little bit later, where the X-ray pulse then probes what is the state, both the electronic and the geometric structure of the material. Then by stitching together such measurements with different time delays, we can create what is amounts to a molecular movie. And here's an example with the very first film, the first movie of a galloping horse, made by Muybridge, Stanford in 1878. And this particular movie solved the mystery of where is the horse? Does the horse legs of the horse ever leave the ground? And until Muybridge's study, this was unknown because the process was too fast to follow with the human eye. And so basically it's the same idea that we can initiate a process and then capture it and make a freeze frame of the process in a time that is short compared to the action that takes place in the process. So how do we do it? Basically, it's we have a sample that consists of a liquid. So we put our molecules in a liquid solution and flow it in a fast-flowing jet, so that between each X-ray pulse, there will be a new sample delivered here to the probe region, so that the intense powers of the X-ray does not ruin the sample for the next time we want to measure it. So in a liquid, we have no long-range order, so therefore we will see diffuse scattering, not to be confused with thermal diffuse scattering, but we will see disordered scattering that corresponds to the characteristic distances between molecules and the characteristic geometries of these molecules in the sample. Then by measuring before and after the optical laser has hit the sample and subtracting the two signals, we will obtain what we call a difference signal. And this difference signal then contains information of what has changed in the sample from before to after we have hit it with the optical light. And analyzing this data then is what lies behind extracting information about the structure of these signals. So how can we do that if we have no crystals? Well, basically, if you think about scattering from a molecule, then it's scattering from an atom that sits here and an atom that sits here. So we could think about it as a diffraction pattern from two scatterers. And you probably know that if we change the distance between the two scatterers, we also change the diffraction pattern. And this change in diffraction pattern encodes the structure of the molecules. So using, for example, the Debye formula to account for the geometric, for the angular rotation that you have in such a system, then we get curves like this. And here I've shown an example for an artificial molecule that consists of two platinum atoms. In one case, you have a distance between them 2.7 angstroms, it's the purple curve, or 2.9 angstroms, that's a yellow curve. Now, if we subtract them, we get the violet curve down here. So this violet curve encodes the distance, encodes the fact that the distance has changed between the two platinum molecules. So if we put this in a solution, we will of course have many molecules, and therefore we can not talk about a crystal structure, but we talk about the liquid structure. And it can, there's many ways to show this, but one example here is how you can get the pair correlation function, the GLM, of the scattering units in the liquid, and compare that and encode this in the scattering signal here. In this case, it's shown for water, which is a notoriously interesting and difficult substance to measure. So how do we do this? So having established the techniques, now we should use them. So here's an example that we did already these 9 years ago. I think we were one of the first European groups that went to the Japanese free electron X-ray laser SACLA in 2011. And it took us these 4 years until we could publish the results, because these are really complicated systems to analyze. So this is a project that we made in collaboration with the chemical physics group in Lund University, that was then led by Professor Wille. So this particular molecule is interesting because it's a prototypical molecule where you have an acceptor, a donor unit centered around the ruthenium atom, and an acceptor unit with a cobalt center. And this cobalt centered unit can be catalytically active. However, cobalt compounds are typically optically dark, so they cannot be measured with using optical techniques normally. But we can measure them with X-rays. And that we did, by using a combination of scattering and spectroscopy. So at the same sample, at the same time, we can measure both the energy distribution of the X-ray emission spectra, the X-rays emitted from the sample, and we can measure the transmitted elastically scattered X-rays directly on a 2D detector. So looking at, so starting out with the model compounds with the cobalt complex in a 3+ and a 2+ state, we can get the corresponding X-ray emission spectra, the blue and the red curve up here. And if we subtract the two, we get the difference. How does the signal change when going from a 3+ to a 2+ state, or 2+ to a 3+ state? So by shining light on the ruthenium, then we can follow how does this change as a function of time since the ruthenium was illuminated, and by looking at that, we get the time scales for the electron transport from cobalt 3, from when the electron arrives at the cobalt 3 and creates a cobalt 2, and that we can then follow by the diminishing intensity in this peak here, and then we get the time scale of the arrival of the electron. And then with some more involved analysis, also involving optical absorption, we can see when the electron arrives here at the connecting bridge, and then build a more complete model where we have an excited cobalt 2 state, which then undergoes a spin flip in 1.9 picoseconds. So the question is then, how does the structure of the system change while we are in this situation? And here we then use the elastic scattering and map the different scattering as a function of the Q vector as a function of time. And you can see when time gets to 0, something happens here at the longer times. So we have a change in the signal. And this we can then decompose into a contribution from the solute molecule and from the solvent, where the solvent then corresponds to the heating that is expelled into the solvent when the molecule relaxes. So we can then simulate how would the structure change, and then use that to fit the data together with a reference measurement of the temperature increase. And by doing that, we can create a picture of what are the processes that goes on here, and then we can see that within 3 picoseconds, this molecule here relaxes, it expands, and in 12 picoseconds, heat is transferred into the solvent. Then we took a closer look at the cobalt complex, because as measurements became more efficient and time resolution became better, we could take a look at what's actually going on in this cobalt complex here when the charge state is changing. And to do that, we also needed to get better data, and we underwent a lot of work to extract information from these rather complicated diffraction scattering signals and also complicated detector signals. But since we could use that we have tens of thousands of images recorded, we can make a kind of statistics that allows us to identify noise and dark current and other effects in the detector, and subtract this from the signal to get a cleaned up signal from our experiment. And using that, we could then make a model that where we allow the structure of this particular complex here to change with the distance between the cobalt and the nitrogens could change as a function of time, and then we could fit this to our total data together with the heating that occurred into the solvent. And by doing that, we could identify not just the breeding mode, but we could actually see what is the distance with atomic resolution between the cobalts and the nitrogens as this structure occurs. And we could then identify 2 modes, where we first have a breeding-like mode that sets in, and then afterwards it's followed by a pincer mode. So this we could then say, well, let's try to use this on some new compounds. How if we now exchange ruthenium with iron, which is basically should be the same, but as you may know, the lifetime of excited state iron complexes is much shorter than in ruthenium, and therefore it's simply too short to avoid that the electron jumps back into the metal center. So in this way, we must do something And we must understand first how are the electrons moving around in the landscape, and what is the effect of the structural relaxation that is also launched by the charge transfer. So by using again combined X-ray emission spectroscopy and scattering, we could follow this in much more detail. And here's the results that you can see that we actually have a coherent oscillation here in the black curve that we could extract from the scattering signal that shows a coherent oscillation between the iron and the nitrogen distances. And at the same time, since we make the experiments at the same time, we will correlate it directly with the intensity in the X-ray emission signal. And this we could then decompose into different electronic states of the molecule. And together, we could then see that we could combine this into a full trajectory of how the molecule responds to excitation. So first we go from the MLCT state to the triplet MC state, and then it goes into the quintet MC state, and then it comes back together with not only an iron-nitrogen distance change, but also a distortion in the geometry of the molecule. And then it goes back, and then it comes down in the quintet MC state. So now we are actually in place to track how does the molecules, how does the excited state trajectory of these molecules evolve. That means that we could also try and look at new compounds that were developed at Lund University, the so-called iron carbines. And in a very similar experiment, we could then follow how does the wave packet that we excite from the ground state into the excited state, how does this evolve on the electronic states? And the key point here is that by changing the conformation of the molecule so that it's now a carbene instead of the tris bipyridine, we simply shift up the electronic states of the quintet state, so that it's no longer. So here before we had the quintet state lying here that allowed for a fast relaxation into the ground state, but now in the new geometry we see that the quintet state is up here, and we only actually populate the triplet MC state as we could see here in our results. So with this we have obtained quantitative information on this excited state potential energy landscapes, which is what is needed in order to have a rational design of better compounds. So my key point here is that the combined result studies where we use both the X-ray emission spectroscopy and the X-ray diffuse scattering or WAX, we can get time-dependent electronic conformation, time-dependent structure. We can measure when the energy is released to the solvent, and we can get the details of the solvent-solute interactions. So with that, I would like to thank you for your attention. I would acknowledge all the people who have been part in developing, making not just these studies, but also developing the techniques that were necessary in order to make these measurements. So thank you very much for your attention.
Thank you. Thank you very much, Martin, for such intense and interesting presentation. We have a couple of questions. One is that you mentioned you were the first European research group on a particular scale of cooperation. What are lessons from that?
That's a good question. I say there's being a first mover is very interesting. It gives you a lot of opportunities. It also gives you a lot of challenges. I would say that if we had, in a way, you could say, if we had been smarter, we would have waited a few years until the techniques were a little bit more mature. On the other hand, you can say it has given us a head start in the field, because we were able to use the limited capabilities of the facilities when they were new. I think that is maybe the key point, that you push the facility to the limit of what it can do, and you try to extract useful information out of that. In terms of these type of experiments and collaborations, as you can see on this slide, there are very many people involved. Some of the publications have 30 co-authors. So that also means that the keeping such a collaboration viable and fruitful is also not something that just happens by itself, but it's something that develops dynamically, and you have to pay a great care and attention to have everybody on board. You say it's maybe also one of the challenges we have in these projects. For example, as a university group, you rely on PhD students, and a PhD student in Denmark has a 3-year project. And as you saw, the time from the measurements to the results were 4 years. That means that you have to come up with ways where you can share your experiment campaigns. You may not be able to have just one campaign for one PhD student, but you will share in joint projects, not just within your own group, but also with other groups. I think that is one of the modes that makes that is one of the cases where, for example, XFEL science can be very difficult to enter for a new group, because it takes a lot of investment in personnel, and it also requires quite some experience to design and execute successful experiments. So there's compared to synchrotron experiments, I would say the barrier for entry is much higher at the XFELs. But I also know that at the European XFEL, we are working very seriously and conscientiously on identifying these barriers, and also maybe coming up with ways to lower them. And I think that is something that will enable this field for more groups, and maybe also other fields of science that has so far not used the free electron X-ray lasers.
Okay, thank you. We have the next question. What are the future prospects of those molecular movie cameras, as you're calling them? What the future prospects they are opening for us? So that's a bit broader question. You can take the scope and scale of the answer on yourself.
Yes. Yeah, I think the prospect is really to see something that has never been seen before. And therefore, you should always be very careful with what is it good for, could you then also ask. And I think what is it good for is, for example, if you want to model what is going on in these processes, then typical ab initio models, they rely on approximations. And if we cannot test in detail how the molecules are behaving, then there is in fact no way of testing the atomistic details in the approximations that we need in order to predict the behavior of molecules. So I think the molecular movie here is really trying to look into the validity and the scope of the approximations that we need to build models of these systems. And if we can put the models on a firmer footing, this also means that we can make stronger predictions about what could be possible new materials. So I think another thing is, for example, if you are aware of the very heated debate on the role of coherence in charge transport, for example, in photosynthetic systems, there has been much debate on why the charges can be transported over comparatively large distances in photosynthetic materials, whereas if you build a photoelectric device, then you're typically limited to a few tens of nanometers. And that's also why you need, for example, the bulk cathode junction structure in your photocells, in your photovoltaics. If you now could understand how the interplay between the structural relaxation and the charge transport, how that works, you could build a model of that. It might be possible to identify systems that could overcome these barriers and so that you could have different geometries, for example, than the bulk cathode junction solar cells. And of course, in basic science, it would be super interesting to know what is the role of coherence in charge transport in general. And it also ties in with other areas of charge transport where coherence could be a factor, for example, in superconductivity. So I think the field is really, how do we understand the phenomena around us? And in order to understand that these ultra-fast charge transport phenomena, we need to know how the charge state is coupled with structural relaxation and vice versa, and how this structural relaxation in turn influences the capability of transporting charge.
Thank you very much for your answers. Martin Midom Nielsen, professor from Technical University of Denmark, thank you for your time and wishing well in further researches. Dear community of scientists and experts, ladies and gentlemen, we are coming to the finish line of the first day of Symposium, and indeed the concluding remarks definitely are around the keywords as a cooperation, working in teams, building teams, and understanding that moving to what we consider as a very important foundations and funds is really possible with this driving force which is cooperation and mutual development. At this particular moment, we remind you again, if you haven't done this, then please do this now. Fill the feedback survey on the first day of the conference. It is in the menti.com. You can see in the left side of your screen down there, 9670848 is the code for the survey. Just go to menti.com and fill the survey. We will be absolutely graceful for that. It's really for future improvements in conference organizing. Nevertheless, while you are filling that, and you have a time to fill it also when this broadcast will be over, we wish you well for tomorrow. Tomorrow is the hackathon, which was already outlined by Mr. Anders Ansvox, the hackathon where you will have a possibility to put your hand on the real exchange of ideas. So if the keyword and the tagline for this particular day was cooperation, then the tagline for the next day is discussion and exchange of ideas, moving further to the real funds, real discoveries in the science, and of course real joy which is coming out from discoveries and the good for society. Thank you very much for being with us today. The questions were just wonderful. The answers were superior. I hope you had a very interesting day. My name is Martin Dauglis, and I'm saying thank you and have a nice evening.